is our basic atomic structure, and as atoms are made up from 3 different subatomic particles: protons, neutrons, and electrons. Protons are in the nucleus and have a mass of 1 and a charge of +1. Neutrons are also in the nucleus, have a mass of 1 but a charge of 0. Electrons are found in the outer shells. Their mass is very small. It's 1/1036 the mass of a proton, and they have charge of -1. When we say the charge is +1, 0 and -1, this is the relative charge compared to other things. The actual charge on this we can measure in coulombs and is very, very small, but it is much easier to say +1 and -1. The mass of protons, neutrons and electrons has been worked out based on carbon-12 as a reference standard. And it is really important to remember that this drawing of an atom is not T-square. It is mainly empty space. The nucleus, the diameter of the nucleus, is basically 10 to the -15 meters, whereas the whole spherical diameter of the atom is 10 to the -10 meters. There is a big difference in those numbers. The structure of the atom has changed over time as new evidence has presented itself. We started off with a blob, basically. An atom means uncuttable. We then went to a solid sphere with negative bits inside it, before we have ended up with today's structure. On the periodic table, you will see boxes with numbers in. Now, it doesn't matter where these numbers are, but the larger number of the two will be the mass number. This is going to be the average mass of the naturally occurring isotopes of that atom, because we can't have half a neutron or half a proton. The atomic number is the smaller number associated with an element. This is the number of protons. You will frequently see the atomic number with the symbol Z and the mass number with the symbol A. Now, the mass number is the total number of protons and neutrons, which is why having a mass number of 35.5 or whatever decimal it is a bit strange. But it can be a decimal because it is an average number of the naturally occurring isotopes. We can have isotopes of an element or different versions of an element. Here we have carbon-12 and carbon-14. They will have the same atomic number, 6. They will have 6 protons, but they will have a different mass number, 12 and 14. This is due to a change in the number of neutrons. We calculate the mass from this by looking at the number of protons plus the number of neutrons. And an increase in neutrons from a 6 to 8 will give us an increase in mass. They will have the same electronic structure, the same number and arrangements of electrons, so they will have the same chemical properties. But their different masses means they might have different physical properties. Here we have a crude diagram of a time-of-flight mass spectrometer. Your unknown sample is mixed with a polar solvent and inserted under high pressure. Ionization will occur by electrons or by spraying. Acceleration will occur by electric field with smaller ions going faster. And here we can use the equation for kinetic energy, half times mass times velocity squared. The speed will depend on the mass and the charge, with heavy things going slower. And the detector will see the ions creating a small charge. This is what we will get as the results. And they can be used to calculate relative mass. The MZ is the mass-charge ratio, and all of these numbers are positive. The mass number that we see on the periodic table is an average of all of the naturally occurring isotopes of an element. We can use the mass spec to work this out. Here we see that 20% of the naturally occurring boron has a mass of 10, and 80% of the naturally occurring boron has a mass of 11. So we can do 20 times 10 plus 80, the percentage, times 11, the mass, divided by 100, which is the total of the percentage. This will give us 10.8 as the relative atomic mass for boron, and this is the number that you will see written on the periodic table. Unfortunately, the structure we have, the picture that you're used to drawing of an atom, is fake. We need to look at the cells, the subshells, and the orbitals. We can look at the periodic table and we can categorize things as D block, S block, F block, or P block, all based on the cells, subshells, and orbitals. And we can draw them like this. So, for example, if we look at calcium, it has 20 electrons. So we are going to start filling from the bottom. Each needs to be filled singly, each electron, and within each box they must have opposite spins. 2 electrons, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That is the electronic structure of calcium, but we can write it out a bit neater. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Here we have a shell. This is a subshell, and this is an orbital. They are very easy to get these confused if you're not 100% clear on what is what. The shapes of the atomic orbitals can be looked at as SPFD. They can be spheres, they can be dumbbells, and all are present at once. We start with 1s and then 2s and 3 2p orbitals. Each orbital can hold 2 electrons. So the total number of electrons in the first shell is 2. In the second shell, it is 2 plus 6, giving us 8. The shorthand way of writing this literally looks at the shells and the orbitals and the number of electrons. So argon's 18 electrons are 1s2, 2s2, 2p6, 3s2, 3p6. And the shorthand for that would be argon in square brackets. Calcium has 20 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, but that's a bit of a mouthful. So we can say argon, which covers that first bit there, 4s2, because it's got the noble gas arrangement. Ions are atoms that have lost or gained electrons. For example, here we see the electronic configuration for calcium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now you can either remember this, which you can do for the group 1 and group 2 as +1 and +2, or you can work it out. Group 1 will form +1 ions, Group 2 will form +2 ions. The transition metals have a variable oxidation state. Group 7 will form -1 ions, and Group 6 will form -2 ions. But they are all aiming for a noble gas configuration. So here we have calcium's electronic structure. It is here. It has these electrons in the 4s2. And to get to noble gas configuration, it is going to lose those electrons one at a time. So it has now formed a +1 ion. Losing another one will give us a +2 ion. And we can change the way we write the electronic structure to reflect that. These are some really important definitions to learn and to make sure you understand properly. The first ionization energy is the energy that is required for the removal of one electron from each atom within 1 mole of atoms in a gaseous form to make 1 mole of gaseous +1 ions. Hydrogen, and using our state symbols gas, will be turned into hydrogen ion gas +1 electron. Sodium, gaseous form, it is really important to get these right, will be turned into sodium plus in the gaseous form +1 electron. The second ionization energy is the energy that is required for the removal of 1 electron from each ion within 1 mole of +1 ions in a gaseous form to make 1 mole of gaseous +2 ions. Our equations, and again it is important to get the state symbols correct here, gaseous. Helium plus will go to helium 2 plus 1 electron. Sodium plus will go to sodium 2 plus in a gaseous form +1 electron. There are a number of factors that affect ionization energy. The atomic radius, where the larger the distance between the nucleus and the outer electrons, the less the attraction will be. Electron shielding or electron repulsion. Electrons are all negative, and the inner ones, the inner electrons, repel the outer electrons, reducing the attraction. Nuclear charge. The more protons in the nucleus, the greater the attraction between it and the outer electrons. If we look at trends in successive ionization energies, we can see some patterns. The first 7 electrons on an outer shell follow a different pattern to the 2 electrons on the inner shell. We can see a big jump here between electrons 7 and electrons 8. There is a big jump in ionization energy. It is always going to get harder to remove electrons, and as electrons are removed, the repulsion between the remaining ones is less. When we are looking at trends in ionization energies, we will see that there is an increase across periods. There is a sharp drop in the first ionization energy between the end of one period and the beginning of the next. And these 2 bits of data give us the evidence for shells. Ionization energy can provide evidence for electron structure. If we look at our graph here, we have increasing atomic number. Here are the groups, and this is the ionization energy. There is a small drop in ionization energy between groups 2 and 3. For example, beryllium to boron and magnesium to aluminium. This drop can be used as evidence for electron configuration. If we look at beryllium and boron, the 5th electron is the first one in the 2p. Because a new subshell has been started, the 5th electron is easier to remove. Another drop can be seen between groups 5 and 6. If we look at nitrogen and oxygen with 7 and 8 electrons, you can see that 8th electron is the first one to be paired in the 2p. So the ionization energy is giving us evidence for electron configuration. There are a few random bits you need to know in chemistry that will pop up all over the place but don't fit into any particular topic. When a question mentions significant figures, give your answer to the same number of significant figures that is the smallest number of significant figures in the question. Any change in that will affect the resolution. Here we have two examples. This one and this one are two different numbers of significant figures. However, this answer here is not the correct answer because it is not to the right number of significant figures. This has the smallest number of significant figures, so this is what we need to mirror in the answer. Otherwise, we are changing the resolution of the answer. We cannot give that to that accuracy because this number is to not that accuracy. If we think back to our GCSE maths, 0.02 can have a wide range of numbers if we're looking at upper and lower bounds. You will frequently be asked to convert between units, especially for temperature. To go from Celsius to Kelvin, you add 273, Kelvin to Celsius minus 273. Centimeters cubed, decimeters cubed, divide by 1,000. Centimeters cubed to meters cubed, divide by a million. Decimeters cubed to meters cubed, divide by 1,000. And the other way around, decimeters cubed to centimeters cubed times by 1,000, meters cubed to centimeters cubed times by a million, and then meters cubed to decimeters cubed times by 1,000. For concentration calculations, if you want to change from moles per decimeters cubed to grams per decimeters cubed, you need to change it by the MR of the substance. These are a couple of important definitions. You will see these phrases used a lot, and it is important that you know exactly what we are referring to when we say these phrases. The relative molecular mass is the average mass of a molecule compared to 1/12 the mass of one atom of carbon. The relative atomic mass is the average mass of one atom compared to 1/12 the average mass of one atom of carbon. You can also see these referred to as AR and MR. A mole is the amount of a substance that contains the same number of particles as the number of carbon-12 atoms in 12 grams. Avogadro's number is the number of particles in a mole. 6.02 times 10 to the 23, quite a lot. Fortunately, you will get given this value in the exam. You don't need to remember it. You do, however, need to remember some equations which we can use moles in. Moles is equal to mass over mR. You might also see this written as N equals M over mR. Mass is in grams and mR is in grams per mole. The number of particles is equal to the number of moles times Avogadro's number. So we could get a question such as this. Calculate the number of particles in 7 grams of gold. We would need to do moles equals 7, that is the mass, divided by the MR of gold, which you can look up on your periodic table. So we have calculated the number of moles. We would then need to take the number of moles and times it by Avogadro's number to give us 2.14 times 10 to the 22 particles. And it is important we look at the number of significant figures here. Here I wrote down all of the significant figures on my calculator. Here I have gone to the same resolution as Avogadro's number. Balancing equations is an incredibly important skill. You will use it in nearly every single lesson. It is definitely worth taking the time to practice this. At A-level, you have to include state symbols in your equations. Even if they don't explicitly ask for it in the question, it is expected. So solid, S, gas, G, L for liquid, AQ for aqueous. You have to include these. So your first step is just going to be drawing circles around the equations. We cannot change anything in these bubbles, but we can change the number of bubbles and then list what you've got in the same order on both sides. It just makes things easier. On the left-hand side, we have 3 hydrogens, 1 iodine, 1 sulfur, and 4 oxygens. Over on the right-hand side, we have 4 hydrogens, 2 iodines, 1 sulfur, and 1 oxygen. So we can see straight away that there is a difference here. The easiest thing to do is to start with increasing the number of oxygens because they're both only in one place on each side. And then redo your numbers. So we have 10 hydrogens, 2 iodines, 1 sulfur, and 4 oxygens. We've fixed the oxygens. We can now move over to the left-hand side and look at something else. Now we could increase the iodines next, but that is just going to cause us problems later on. So we're going to look at the hydrogens. We have 2 hydrogens in sulfuric acid and 8 in the hydrogen iodide, giving us 10 in total, 8 iodines, 1 sulfur, 4 oxygens. So now our hydrogens, our sulfurs, and our oxygens are balanced. We can just put 2 in front of the iodine and balance that as well. This is a vitally important skill. You need to practice this so you can do it quickly. After you've done your working out, always write the equation out in full so it is clear to the examiner exactly which bit they should be looking at. There are lots of equations where moles come up, and they can be used to switch from one equation to another equation as an intermediary. So this is just a summary slide of all of the equations that use moles. We have the ideal gas law, so PV equals nRT. The concentration of solutions, so N for moles equals concentration times volume. The equation for mass, where moles is mass divided by mR. And looking at the number of particles, where it is moles times the Avogadro number, the constant. So you can go from one place to another place using the ratio of moles. So we can go from the number of particles to the volume this way, or we can go from volume over here to mR. For the concentration of solutions, we need to know that concentration equals mass over volume. Concentration is measured in grams per decimeter cubed, mass in grams, and volumes in decimeters cubed. For ionic solutions, you need to remember that there are 2 different ions in there. For example, calcium 2+, and 2 chlorine ions here. So from 1 mole of calcium chloride, we will get 1 mole of calcium ions, but 2 moles of chloride ions. The same is true for acidic solutions, and this is important for titration calculations. Sulfuric acid, for every 1 mole of sulfuric acid, we will end up with 2 moles of hydrogen ions. The first required practical you will do is one you will become very, very familiar with. It is making a standard solution and then doing a titration. These are skills that come up over and over again. When you're making a standard solution, the thing that is most important is that you want to be very, very accurate. So you can see in this video here, I've weighed out my powder into the weigh boat, and then I'm continuously washing the weigh boat to get all of the powder off the weigh boat. And then it is in the beaker where I'm mixing it. And what I'm going to do is to wash the sides of the beaker to get all of the powder that might be on the sides of the beaker actually into the flask. We're going to keep washing because we need to fill this flask all the way up to 500 mils or 250 mils or whatever it is. Just wash everything out. So now I'm washing the flask out, and then we just need to swirl it a little bit and then make it up to the volume that we were looking for. You can see I'm washing the neck in case any powder has got down the neck of the flask. We're going to invert it a little bit to make sure it is properly mixed and wash the neck again. The aim is to get all of the powder that you have weighed out into solution. Now you'll see the little line on there. You want to go up to that line, but do not go over it. So at the end, we can go drop by drop. The temptation, if you go over it, is to remove some. Do not remove any from your standard solution. If you go over, you're going to have to start again. If you go over and then remove some, you are removing some of the powder that you have weighed out. So you are changing the concentration of the solution. So if you go over, do not remove any. That would be one source of error. Care is key when you are doing a titration. You need to take care on every single step because there are lots of different possible sources of error. You might have a bit of confusion reading the numbers on the burette, or you might have a bubble in your tap. You might go over the end point by a couple of drops. You need to do this super slowly. A good thing to do is to always start with a rough titer, so you know roughly the number that you're looking for, so you can go fast for the first part and then slow down. We are looking for concordant results, and when I say concordant results, I mean results that are within 0.10 centimeters cubed of each other. You would be aiming for 3 concordant results, and when you get practiced at this, you can do a rough titer and then 3 actual titers, and your 3 actual titers will be concordant. You can record all of your results to 2 decimal places. When you see a titration calculation, there are some very specific things I want you to do first of all. First of all, is highlight all of the information in the text, and then we're going to pull out that information. So it is all in one place when you need it, and you don't have to trawl through all of the information again when you're trying to answer the question. So we need the volume of acid, the concentration of acid, the volume of the alkali, and the concentration of the alkali. Concentration of the alkali is X, that's what we're going to put in there, and the rest of it we're going to grab from the question and write it down so it's easy for us to find later. With all of the information in one place, we don't have to dive back into the complicated text to find out what we need when we need it. We're also just going to note down the equations that we are using to help us so that we don't get confused trying to think of things, trying to remember when we are deep in answering the question. The first thing you need to do for this is to write a balanced equation. So we have sulfuric acid and sodium hydroxide, making our sodium sulfate salt and water. Step 1 in any titration calculation is to find your moles of known. Here we know the acid, so that's what we're going to be finding the moles of, and we're going to be using the numbers that we have pulled out earlier. So moles equals concentration times volume. We need to adjust the volume so that we are working in litres, because this is in centimetres cubed, giving us 0.0025 moles of hydrogen ions. We then need to find the ratio of hydrogen ions to hydroxide ions, and because of the ratio in the balanced equation, it's doubled. We can then use moles, concentration, volume. We have the number of moles, we have the volume, so we can find the concentration of the alkali. The question is asking for the answer in grams per decimeter cubed, so we need to convert our units. The first thing we need to do is to find out the mass of sodium hydroxide. Using moles times mR, we can get our answer in grams per decimeter cubed. Whenever you have anything reoccurring, 1.6 reoccurring for example, always use your calculator value, otherwise you're going to be introducing rounding errors into your answers. We use the ideal gas law a lot, and you need to remember this equation. PV equals nRT. P stands for pressure, V is the volume, N is the number of moles, R is the gas constant. You need to remember it's gas constant, but you don't need to remember the value for it. You get given that in the exam. And T is the temperature. Pressure is measured in pascals. Volume is measured in meters cubed. The gas constant is 8.31 joules per mole per Kelvin. Temperature is measured in kelvins. Now the conversions for this is often where people go wrong. Determine the mass of a 500 centimetre cube sample of hydrochloric gas when at 20 degrees C under 150 kilopascals pressure. For any calculation question, the first thing I like to do is to highlight all the numbers and then pull them out of the question and write them down separately. Some questions can be very wordy, and having the numbers that you need right there in front of you can make things a lot easier. We can then see which ones of these are in non-standard units and convert them into standard units before we start. So pressure was given in kilopascals and we need it in pascals. So 150 kilopascals is going to be 150,000 pascals. Volume was given to us in centimetres cubed and we need it in metres cubed. To go from centimetres cubed to metres cubed, we need to divide by 1 million. And temperature was given to us in degrees Celsius and we need it in Kelvin. And to do that, we need to add on 273, giving us 293 Kelvin. We can then use the equation, and the first thing we're going to find out is the number of moles. So we can rearrange the equation to give us N equals PV over RT and then plug in the numbers. Once we have the number of moles, we can use mass equals moles times MR to give us the number of grams, to give us the mass that the question is looking for. When we are looking at the volume of gases, it is important to remember that 1 mole of gas under room temperature and room pressure will occupy 24 decimeters cubed. And we can use P1 V1 equals P2 V2, pressure and volume, at a constant temperature to determine volumes. So determine the volume of 1 mole of gas would occupy if the pressure was doubled to 2 atmospheres at room temperature. Because we know the pressure was doubled, P2 is 2 atmospheres, which means P1 is half of 2 atmospheres, giving us 1 atmosphere. We know from laws that this is 24 decimeters cubed volume. The second pressure is 2, so 24 equals 2V2. We can then use algebra to move the 2 over to the left-hand side, giving us 12 as the new volume. There is a difference between the molecular and the empirical formula. The molecular formula will give us the exact number and identity of each element in the compound. The empirical formula will give us the simplest whole number ratio of the elements within that compound. In an exam question, we might see something like this. A compound of phosphorus 5 oxide has an MR of 284 and is made from 62 grams of phosphorus and 80 grams of oxygen. Calculate the empirical and molecular formula. This is how I want you to set it out. Very strictly, if you do it like this, we shouldn't come up across any problems. We're going to start by making a table with your element, the number in the question divided by the AR equals the whatever number it equals, divided by the lowest number, and this is going to give us the ratio. If we follow this format here, we should be fine. So the elements in the question, phosphorus, oxygen. Find the numbers in the question. It doesn't matter whether it's grams or percentages or anything. Find the numbers in the question and write them down in the appropriate place. We then need to divide that by the AR, and you can get the number from your periodic table. And whatever your periodic table says, use the number that it gives on there. Don't use the whole number or any other number. Use the number it gives on your periodic table. There's a number here, and then we need to divide it by the lowest number. The lowest number out of these two is 2. So we're going to divide both of these by 2. 2 divided by 2 equals 1. 5 divided by 2 equals 2.5. Because 2.5 isn't a whole number, we need to multiply it by 2 to get the ratio. So P2O5. This is the empirical formula. Now we know the MR of this is 284. So we need to start by working out the MR of the empirical formula that we worked out, P2O5. So this is our mass from the periodic table, and these are the numbers that we have in the empirical formula. This gives us 142. We take the MR from the question, 284, divided it by 142. It means there are going to be 2 lots of the empirical formula in the molecular formula. Thus, we are going to have P4O10, and you can quickly check that that does add up to the right amount. Often in a reaction, there is a difference between how much we think we're going to make and how much you actually get. This is called the percentage yield. We can calculate percentage yield by dividing the actual yield by the theoretical yield and multiplying it by 100, so we get a percentage. It was expected the reaction would give 14 grams, instead it gave 5.2 grams. Calculate the percentage yield. 5.2, the actual yield, divided by 14, the theoretical yield, times 100, gives us 37% as the percentage yield. There are a number of reasons for a lower than expected percentage yield. Reactions do not always go to completion. Some of the reactants just don't react and are left over at the end. There could be a loss of product. It could be difficult to collect. It could be hard to collect it safely. It could be difficult to separate it from the unreacted reactants. There could be side reactions occurring that were not predicted at the beginning, giving you products but not the product that you want. Atom economy. When you do a reaction, you will end up with a certain mass of stuff at the end, the mass of the products. But not all of that is actually useful. Some of it is going to be waste and some of it is going to be useful. So we can calculate percentage atom economy by looking at the mass of useful products divided by the mass of all reactants, and because it's a percentage, we times it by 1,000. Atom economy can be improved in 2 different ways. We can find an alternative reaction pathway that has less waste, or by finding uses for the waste products. From a reaction, you need to be able to work out if something is in excess or if one of the reagents is limiting the reaction. As with everything, we need to start off with a balanced equation and work out the masses of everything. We can see from the balanced reaction that 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide, which turns into 1 mole of sodium sulfate and 2 moles of water. This is balanced. However, in practice, it might not always be like that. For example, we have 11.76 grams of sulfuric acid reacting with 2.4 grams of sodium hydroxide. Work out which one is the limiting reagent. And this is the equation that we are going to be using. So for sulfuric acid, we have the mass, so 11.6 divided by the MR will give us 0.12 moles of sulfuric acid and 0.06 moles of sodium hydroxide. If we divide by the lowest number to get the ratio, we will have 1 mole of sodium hydroxide with 2 moles of sulfuric acid. This doesn't match up with the equation, with the moles we worked out from the equation, so it will tell us which one is the limiting reagent. When we are looking at a hydrated salt, we can talk about the water of crystallization. For example, here we're going to look at hydrated and anhydrous copper sulfate. They are different colours, and the formula can reflect whether it is hydrated or anhydrous. The anhydrous form is white. Here it is as a white crystal. You can then add water to it and it will go to the blue crystals that perhaps you're a bit more familiar with. We can then turn it back to the anhydrous white crystal by heating it again. The anhydrous salt will have the formula of CuSO4, whereas the hydrated copper sulfate is CuSO4 dot, this dot in here, 5H2O. This is a reversible reaction because upon heating or adding water, you can get the salt to change forms. You might be asked to do a calculation based on this in the exams. Here we have 7.5 grams of hydrated aluminium 3 nitrate, which was heated, and 3.24 grams of water was lost from the sample. Determine the formula. The first thing we need to do is to determine the formula of the aluminium 3 nitrate. Aluminium is a 3 plus ion, nitrate is a minus ion. That is going to give us aluminium, open brackets, NO3, close brackets, 3. Then we can write in the dot X, because that's the bit we're trying to find out, H2O, trying to find out the formula of the hydrated salt. We can work out the mass of the anhydrous salt by taking the mass of the hydrated aluminium nitrate and removing the water, giving us 4.26 grams. We can then go to an empirical formula, where same format, we have what is in the question, we have the numbers in the question, or the masses. We're then going to divide that by the MR. Now water, I know this because it's 18, but aluminium nitrate, I do have to do a calculation to work out. When working out MR, always use the numbers given for mass on your periodic table. If we divide the mass by the MR, that will give us the number of moles for each of these. We can then work out the ratios. So how many waters were there for every aluminium nitrate? That is just dividing it by the smallest number. So for every 1 aluminium nitrate, we had 9 waters, giving us X equals 9, and the formula Al, open brackets, NO3, close brackets, 3.9H2O. Depending on the equipment that you use for something, or the size of the equipment that you use for something, there will be different levels of uncertainty involved. For example, here we have 3 measuring cylinders which can measure different volumes. So the first one, the divisions are 4 centimeters cubed, and the reading on it is 100 centimeters cubed. The second one, the divisions are 2 centimeters cubed, and the reading is 70 centimeters cubed. For the third one, the divisions are 0.2 centimeters cubed, and the reading is 6 centimeters cubed. The uncertainty involved in each is half a division. So for the first one, the reading could be plus or minus 2 centimeters cubed, plus or minus 1 centimeter cubed, plus or minus 0.1 centimeters cubed. However, any experiment is more than likely to involve several stages, several measurings, thus several levels of uncertainty. To work out the percentage uncertainty, it is plus or minus the uncertainty divided by the measurement times 100. The total percentage uncertainty in any experiment is the sum of all the individuals. For ionic bonding, we need metals and non-metals. And we can call this the transfer of electrons from a metal to a non-metal, resulting in a positive metal ion and a negative non-metal ion. Between these two ions, there will be an electrostatic attraction, and this is what we call an ionic bond. If we look at magnesium chloride, magnesium has 2 electrons in the outer shell, and chlorine has 7 electrons in the outer shell. Magnesium will transfer 1 electron from its outer shell to each chlorine's outer shell. We can draw this using square brackets and having the charge on the outside of these square brackets. This will give us the formula MgCl2. If we compare the electronic configurations of the atoms and the ions of both magnesium and chlorine, you will see that magnesium has lost these 3s2, so it is bringing it down to full shells, whereas chlorine has 3p5, and it wants another one to make this 3p6 to make it more stable. This formula can be confusing. It is important to remember that the magnesium, the chlorine, will not just be attracted to the ion it gained or lost electrons with. All ions will feel this force, not just single ones. Electrostatic attraction is stronger if ions have higher charges or if they are smaller. It is expected that you know the formula of ionic compounds, or at the very least can work them out from the periodic table. Ions of group 1 elements are going to form +1 ions. Ions of group 2 elements are going to form +2 ions. Ions of group 6 elements are going to form -2 ions, and ions of group 7 elements are going to form -1 ions. However, the transition metals have variable oxidation states, and you also need to know the formula and the charges on some of the complex ions. We can look at a couple of examples of forming the formulas of ionic compounds from knowing what the individual ions. Sodium carbonate. Sodium is going to have a +1 charge, and carbonate has a -2 charge. Since overall sodium carbonate has no charge, we need the positive and the negative charges to balance each other out. The Roman 3 in ion 3 means it has a +3 charge, and sulfate has a -2 charge. Now iron sulfate overall has 0 charge, so we can look at this by doing 3 times 2 and just kind of swapping them over. So because iron has a 3+ charge, we're going to need 2 of those to get to +6. And because sulfate has a -2 charge, we're going to need 3 of those to get to -6. Giving us the formula of Fe2 open brackets SO4 close brackets 3. Often you'll be given a word equation and expected to construct the balanced equation from that. And knowing your general salt equations is a really important part of being able to do that. A metal plus an acid will give us salt plus hydrogen. A metal oxide plus acid will give us salt plus water. A metal hydroxide plus acid will give us salt plus water. A metal carbonate plus acid will give us salt plus water plus carbon dioxide. Using hydrochloric acid will give you chloride salts. Using sulfuric acid will give you metal sulfate salts. And using nitric acid will give you metal nitrate salts. At the heart of this is the neutralization equation, which comes up a lot. Aqueous hydrogen ions plus aqueous hydroxide ions in a reversible reaction with water. If you struggle to work out the products of a reaction, it helps to break it down into ions. So sodium hydroxide plus hydrochloric acid. The sodium ions and the chloride ions will give you the salt, sodium chloride, and then the water will be formed from the hydroxide ions and the hydrogen ions. Covalent bonding occurs between non-metals. It is the sharing of electrons between two non-metals. When we are drawing it, a single bond is one pair of electrons being shared. A double bond is 2 pairs of electrons being shared, so 4 in total. A triple bond is 3 pairs of electrons being shared, 6 electrons in total. When we are drawing things at A-level, circles are optional, and I will draw them from now on without circles. So here we have oxygen, X is from one, O's from the other. We have 4 electrons, or 2 pairs in the middle, making our double bond. For nitrogen, we will have 6 electrons in the middle, or 3 pairs. In dative covalent bonding, one element gives both electrons for the bond. Here we have ammonia with its lone pair of electrons up here at the top. A hydrogen ion has no electrons to share, so when it bonds with it, to form an ammonium ion, all of the electrons will have been donated by this nitrogen here. This hydrogen that joined did not give any electrons to this, and we draw that with an arrow. Here is another example. In the bonding here, this bond here, all of the electrons will have been provided by the nitrogen. The boron didn't provide any of these electrons, so this bond here is a dative covalent bond, whereas the rest of them are traditional covalent bonds, giving us NH3BCl3. Here we have our model of metallic bonding. We have blue positive metal ions. In green, we have the delocalized electrons, which are free and kind of floating around. The electrostatic attraction between the delocalized electrons and the positive ions leads to bonding. The stronger bonding will happen with smaller ions, more delocalized electrons, and a more positive nucleus. When we are thinking about the properties of organic structures, it is really important that we think of these as a lattice, a large structure. Here we have sodium chloride, and we write it as NaCl, but it is massive. It's not just one sodium and one chlorine. Each sodium plus ion is surrounded by 6 chlorine ions, and each chloride ion is surrounded by 6 sodium ions. All of these are attracted to each other and weakly attracted to the ones that are further away. The attraction is lattice-wide, not just to the one that donated or received the electrons. Giant ionic lattices will have high melting points and high boiling points. This is because the strong electrostatic attraction requires large amounts of energy to overcome that strong electrostatic attraction. They will be soluble in water. Water is polar, it will interact with the ions on the outside and pull them off. They will conduct electricity when molten or dissolved, because the ions can move freely, whereas in a solid they cannot. The solids are hard and brittle as the ions are fixed in place and not free to move around. Giant metallic lattices have a few particular properties. They have high melting and boiling points, as their strong electrostatic attractions require lots of energy to overcome them. They're insoluble in water. They will conduct when solid or molten, as in both forms the electrons can freely move around. They can conduct both electricity and heat. They are ductile and malleable because the metal ions can slide over each other. You need to know the properties of giant covalent macromolecular structures, and we are going to use silicon dioxide as an example. These giant covalent structures will have high melting and boiling points because the strong intramolecular bonds require large amounts of energy to overcome them. They're insoluble in water. They are poor conductors, as the electrons are not freely available to move around. Diamond and graphite are special examples of giant covalent structures. They are both made from carbon. In diamond, each carbon makes 4 carbon-carbon bonds, whereas in graphite, each carbon makes 3 carbon-carbon bonds. Diamond is very hard in a lattice structure. Graphite is soft as the atoms are arranged in layers that can slide over each other. Diamond does not conduct electricity. All the electrons are involved in bonding and there are no free electrons. Graphite does conduct electricity. There is a free electron that is not involved in bonding, meaning it can move around and conduct. When we are talking about simple molecular structures, covalent ones, there are some common examples that you should be familiar with. Water, H2O, ammonia, NH3, nitrogen gas, N2, carbon dioxide, CO2, and oxygen gas, O2. Obviously, there are lots more examples, but these are common ones that you should be very, very familiar with. Simple molecular substances will have low melting and boiling points due to weak intermolecular bonds. They are insoluble in water. They do not conduct. There are two commonly confused, because of the spelling, types of bonding here. We are going to look at covalent intramolecular bonds, which are the strong covalent bonds between atoms in a compound. These are very, very strong. And then there are the weaker intermolecular bonds. These ones are much easier to overcome and give rise to properties such as the low melting and boiling points. You need to know the shapes of lots of different molecules, or at the very least be able to work them out. So here are some examples. We have carbon dioxide, HCN, BeF2, and these are linear. The bond angles are going to be 180 degrees, and there are no lone pairs. I'm going to be using molemods to show you these. If you are confused about this topic, I strongly suggest that you get yourself a set of molemods and actually sit there building these and playing with them. You can see how the shape is linear, how the bonding sets up, and then we can draw the dot and cross diagram down here and relate it to the stick diagram with the 180 degree bond angle. For SO3, BCl3 and AlCl3, these are trigonal planar. They will have bond angles of 120 degrees, and these have no lone pairs. They are flat, and we can see the bonding here. For CH4 and NH4+, these are tetrahedral. They have bond angles of 109.5, and there are no lone pairs. When we are drawing 3D structures, a line like this shows it is in plane with the paper. Here we have backwards and then forwards. So we can have two bonds in line with the paper, one coming forwards out of the paper and one going backwards into the paper. And it is much easier to see if you actually have this in your hands and you can hold it and you can align it so that you have the bonds in plane with the paper, going backwards and going forwards. If we just have the dot and cross diagram over here, it is really hard to see how the bonds are arranged. For NH3 and ClO3, these are trigonal pyramidal. Their bond angles are 107, so roughly 2.5 less than that of tetrahedral, and they have one lone pair, which is shown in pink here. Adding on the lone pair really helps to remind you that the bond angles are different compared to this structure here, where it's a bit hard to see. And you can see we have one bond in plane, one forward and one backwards. Water, H2O, is a bent shape. It has a bond angle of 104.5. That is 2.5 less than trigonal pyramidal, and it has two lone pairs, again shown here in pink. It really helps to remind you, if you add in the lone pairs compared to water without the lone pairs, that the bond angle is going to be reduced due to the valence electron theory. The lone pairs can be seen here on the dot and cross diagram. PCl5 is trigonal bipyramidal. It has two different bond angles of 120 degrees and 90 degrees. There are no lone pairs. The bond angles are really easy to see the difference in the 3D structure using molemods, but much harder to see it when you are drawing it out in the 3D way or even in the dot and cross diagram. If this is something you struggle with remembering, then either using molemods or flashcards, because this is something that you need to be able to remember. You will notice that around the phosphorus in the middle there are 10 electrons. This is an expanded octet. SF6 is octahedral. All of the bond angles are 90 degrees and there are no lone pairs. We can see this in the 3D model. We can see this when we are actually holding the molymods in our hands, that the bond angles are 90 degrees, whereas on here it is much harder to visualize these being 90-degree bond angles. This is another one with an expanded octet around the central atom. VSEPR theory is a bit of a mouthful, but then so is valence shell electron pair repulsion theory. Electrons are negative and they repel each other, so the electrons on the outer shell arrange themselves so they are as far apart as possible. Here are some examples. Each of these has 4 pairs of electrons in the outer shell. CH4 has 4 bonding pairs. NH3 has 3 bonding pairs and 1 lone pair. H2O has 2 bonding pairs and 2 lone pairs. So while they all have 4 pairs of electrons in the outer shell, they have different bond angles. CH4 will have 109.5 degrees in our bond angle, NH3 will have 107, and H2O has 104.5. This is because lone pairs are more repulsive than bonding pairs. When you increase the number of lone pairs, the bond angle decreases. A lone pair is more repulsive than a lone pair bonding pair is more repulsive than a bonding pair. Electronegativity is a measure of how much an element will attract electrons. We have fluorine over here as the most electronegative element. As we move across a period, the electronegativity will increase as the number of protons increases. In a period, the number of electron shells remains the same, so the atomic radius is decreasing as the electrons are pulled in. Electronegativity decreases as we move down groups. The increasing number of shells increases the shielding around the nucleus. Covalent bonding and ionic bonding are not completely different things. There is a spectrum, and that goes for increasing polarity. When 2 elements are the same, we can have pure covalent bonding with the electron cloud shared evenly. If we have different elements in a covalent bond, then the electron cloud may be shifted more towards one side. And as the polarity increases, the shift of the electron cloud is going to increase as well. Until we get to the point where the electrons have been transferred and we have ionic bonding. For lots of these, partial dipoles will be set up within the bond. And this can all be due to the difference in electronegativity. If there is more than a 2 difference in electronegativity, then we're going to be seeing ionic bonding. Sharing electrons is a continuous spectrum with covalent bonding at one end and ionic bonding at the other end. And for example, in hydrogen gas, we have equal electronegativity between these 2 elements, so they share electrons equally. In HCl, the chlorine is more electronegative, so it's going to attract the electrons more, and our electron cloud is going to be shifted, setting up a dipole. When we are talking about permanent dipole forces always use the full wording, even though it might seem repetitive and a lot to write out in the exam. This is what the examiners expect to see. Some molecules are made up from atoms with different electronegativities. For example, HCl, And the electron cloud here is not going to be even. It's going to be shifted more towards the chlorine, which is more electronegative. This is going to set up a bond polarity, and we can have permanent dipoles. Now, in a large collection of HCl molecules, they will all have these dipoles, and this will result in attractions between the delta negative and the delta positive parts. This will result in a higher melting and boiling point. As the intermolecular bonding is stronger, we can see this as HCl is asymmetrical. For a symmetrical molecule, the forces are going to balance each other out, and it will not be polar. When we are looking at induced dipoles, they can be referred to as dispersion forces, London forces, or London dispersion forces. But because I'm old-fashioned, I will refer to them when I'm doing my work as induced dipoles, instantaneous dipoles, which is much more descriptive of what they actually are. This type of dipole will occur in most things, but not in ionic substances. Here we have a chlorine molecule, and it has an evenly shared electron cloud. The electrons are evenly distributed between each atom, but they are always moving around. The random movement means that at any point they can all be around one atom and not the other, meaning a dipole will instantaneously form. This will induce a dipole in a neighbouring molecule. The strength of these forces will depend on the number of electrons. The more electrons involved, the stronger it will be. The shape of the molecule. The more surface area that allows more contact, the stronger the forces will be. For example, between these two linear compounds, there are lots of opportunities for contact. Whereas in the branched isomer, there are much fewer opportunities for contact, meaning the strength is going to be reduced. Straight isomers will have more contact points, meaning the intermolecular forces will be stronger and they will have a higher boiling point. Hydrogen bonding is an area where we see a lot of crossover with biology. It occurs when hydrogen is bonded to either nitrogen, oxygen, or fluorine, right over here in the very electronegative area of the periodic table. Between these two elements, there is a large difference in electronegativity. At the same time as hydrogen bonding, you can have other forces occurring, such as van der Waals. But hydrogen bonding is stronger than the other intermolecular forces, and this leads to a few properties. They will have anomalously high boiling points. And we will see in water that ice is less dense and water has a very high specific heat capacity. How we use words and definitions are important, so here we're going to be looking at enthalpy change. During a reaction, heat energy can be taken in or given out. This is the enthalpy change. It is given the symbol delta H. Delta, whenever you see this triangle just means change in. H is enthalpy, so delta H is change in enthalpy. This shows us we are looking at the enthalpy change under standard conditions. If we have a negative delta H, we are going to have an exothermic reaction. Heat energy is given out. A positive delta H is an endothermic reaction. Heat energy is taken in. An endothermic reaction will get colder while an exothermic reaction gets hotter. Enthalpy change is measured in kilojoules per mole. Enthalpy profile diagrams can tell us a lot about what is happening in a reaction. We have energy going up the side, and the reaction going along the bottom. The products and reactants are labelled with their different amounts of energy. If the reactants have more energy than the products will have less energy than reactants. Energy is released. This is an exothermic reaction. Or we can say that delta H is negative. On the other side, the products will have more energy than the reactants. Energy is absorbed. This is an endothermic reaction. Delta H will be positive. Many reactions will have an activation energy, the hump of energy that is required for a reaction to start. Here it is in green on the diagram. You will see chemists talk about standard conditions a lot, and it is important that you know what they are. We use standard conditions because lots of reactions will change with a change in temperature or pressure. For example, the reaction could get faster at higher temperatures. So whenever you see values given in a calculation, these values will change as well depending on the temperature and the pressure. So they are generally given under standard conditions, and you will be told this. The temperature is always considered to be room temperature, so 25 degrees Celsius or 298 degrees Kelvin. The pressure is 1 atmosphere pressure, which is atmospheric pressure. This is also 100 kilopascals. When we are talking about the standard enthalpy change of combustion, this is the enthalpy change that occurs when 1 mole is burnt completely in an excess of oxygen under standard conditions. We can write that in shorthand here. We have delta for change in, little c showing it's a combustion, H for enthalpy, and under standard conditions. These values are generally going to be exothermic because it is combustion, or if something doesn't burn, then 0. When we are talking about the standard enthalpy change of formation, this is the enthalpy change when 1 mole of a substance is formed from its elements under standard conditions. For this, everything needs to be in their standard states. Here is our shorthand again. Delta for change in, F for formation, H for enthalpy, and under standard conditions. This value can be positive or negative. It can be endothermic or exothermic. We can look at the enthalpy change of a reaction using calorimetry. Notice the spelling, calorimetry, not colorimetry. The equation for this is energy change equals mass times specific heat capacity times the change in temperature. And the change in temperature is the bit where we can actually get hands-on and measure this in a lab. We can also measure the mass. We generally know the specific heat capacity, so we can work out the energy change that has gone on. For energy change, we're going to be using joules. For mass, we're going to be using grams. For temperature, we're going to be using Kelvin. Your datasheet should be able to help you with this. If delta H is negative, it gets hotter. If you have a positive delta H, it will get colder. Measuring the enthalpy change of a reaction is a required practical for your A-level. There is a more detailed video that you can go and watch of this, but very briefly here it is. You are going to need to make some nice tables because you're going to be doing a lot of recording at times. You are going to need to record at which point you add in the powder to the solution or mix your two solutions. You are going to need to know the mass that you are adding so we can add this into our calculations. The beaker is to make sure it's steady. The polystyrene cup is for insulation, and we need a thermometer so we can actually record the temperature. You can measure the temperature change of a reaction over a period of time. Here is when we added in the powder to the solution, so we couldn't take a measurement there, but we can draw a graph of time, skipping the one where we added it in, and you will see through this we need to draw a line of best fit. It's not going to look beautiful because temperature drops in intervals, and then we need to go backwards, find 0 and extrapolate back what the maximum temperature reached was. Then we can put that into our calculations. If you've got 2 of them, you can combine these and follow the instructions. This will allow you to find the maximum temperature reached, or the temperature at 0, which is difficult to do as you're doing it, difficult to find the temperature at 0 because you are currently busy adding things in. This experiment can be improved by using a data logger, which will continuously monitor the temperature over time, and it will even draw your graph for you. Errors might occur when we have energy loss to surroundings. A lid or the polystyrene cup helps with that, or the reaction could be incomplete, thus you wouldn't get a true reading. Hess's law is a subject I really enjoy. I think it's really elegant, and I have done lots and lots of other videos full of examples to help you work it out if this summary slide doesn't make it clear for you. This follows the first law of thermodynamics, that energy is always conserved. So if we're going from the start to the end, it will always take the same amount of energy to get there. It doesn't matter which path you take. The enthalpy change for any reaction depends on the initial and the final points, and is independent of the reaction pathway. We can use this to find the enthalpy change of reactions that we can't measure by using data from reactions that we can measure. So for the enthalpy change of combustion, we have our reactants going to our products. But as an alternative path, we have our combustion products. And I always draw boxes around these. That's just the way that I was taught to do it. If we burn our reactants, we will get the combustion products, and if we burn our products, we will get the combustion products. So if we want to find information going from reactants to products, we can use the combustion products as a bypass. We can't directly measure carbon and hydrogen going to methane, but we can know the data for the combustion products. The combustion products being carbon dioxide and water. I always lay it out by writing on the data. So here we have carbon and 2 lots of hydrogen gas combusting. Notice these are negative values and the units are kilojoules per mole. Now this is the path that we are going to be taking. I always encourage my students to draw this on in a highlighter or a coloured pencil so you can see it. Now for the start, we are going in the same direction as the arrow, so the signs are the same. Minus 394 plus 2 times minus 286. For the other parts, we are going in the opposite direction, so the sign is opposite. Plus 890 gives us an overall value of minus, because it's exothermic, 776 kilojoules per mole. Enthalpy change of formation looks very similar. These are formed from the elements, so that is what we have at the bottom. Except that arrows here go in the opposite direction because this is formation from elements to the reactants and from elements to the products. Here is another reaction we can't directly measure, but we can look at the formation from the elements down here. Now remember, this needs to be balanced, so we have 3 lots of hydrogen and half oxygen gas. Draw in your arrows, add on the data, draw with colour pen or highlighter the arrow that you are going to be following. Notice this one here is now in the opposite direction. We're going in the opposite direction to arrow. So this one is the one we need to change the signs for. Different direction, different signs. Same direction, same signs. So it is now plus 75 and plus 242 minus 110, same signs, different signs. Always remember to put the positive or negative on here and add in your units. When we talk about bond enthalpies, we mean mean bond enthalpies because each of them will be slightly different. So the value that we use is the mean averaged across the lot. Bond making is exothermic. Bond breaking is endothermic. To work out delta H, it is the energy to break the bonds in the reactants minus the energy to make the bonds in the products. That is the energy that we released or given out, taken in during the reaction. Here is our example, and I always encourage my students to draw out what they can see. It makes you take note of the actual bonds that are involved and is less likely to cause mistakes later on, especially when we get to something like water, because there are actually 4 bonds involved, and it is much easier to see those 4 bonds if you draw it out fully. And then start very methodically to label this out. So here is our bonds, here is how many we have of them, and then you can pop in the data that you are given for the question. Either number or tick off each bond once you've counted it to make sure you do not miss any out. You can see here, quickly going through the calculations, that I am laying this out in a very clear and methodical way, making it very easy for the examiner to see what I've done, to see potentially if there are any mistakes in writing any of these numbers down, so that if there was a mistake, an error carried forward could be given. Always, please, always lay your calculations out as clearly as possible and give the examiner instructions as to what is actually happening. We can then do the final calculation and work out the answer. This is an exothermic reaction because it is negative. Always with this type of calculation where you can have negative and positive numbers, add in the sign and the units. Collision theory is simply that reactions will happen when particles with sufficient energy collide. Here we have our reaction profile with our reactants up here and our products down here. It could also be that the products could be up here for a reaction. This energy here is the activation energy, the energy needed to get a reaction started. For a reaction to take place, it could be either making bonds or breaking bonds or a combination of these, depending on what reaction it is. The rate of a reaction will change depending on the temperature, the concentration, the pressure, or if a catalyst is involved. We can use a Maxwell-Boltzmann distribution curve to look at the energy that particles in a reaction have. Up the side here, we have particles with that energy. Lots of different graphs will say number of particles, fraction of particles, percentage of particles. It is just the amount, horrible word, of particles with that energy, and energy along the bottom. We will have some particles with low energy over here. The peak is the most probable energy, slightly shifted from the mean energy. The area under the curve is the total number of particles. And here we have the activation energy. There is no maximum energy that a particle can have, and it will go through the origin since there are no particles that have no energy. The particles in this bit here that have passed the activation energy, these are the ones that will react. If we increase the temperature, we will shift the curve. Now, more particles have passed the activation energy, increasing the numbers that are available to react. A catalyst will shift the position of the activation energy by providing an alternative route. temperature has an effect on the rate of reaction. Here we have our Maxwell-Boltzmann distribution curve with our original temperature, T1. T2 is an increase in temperature. If the activation energy lies here, we can see that shifting the temperature to T2 means more particles now have enough energy to overcome the activation energy. Roughly a 10% increase in temperature will double the rate of a reaction. As well as more particles having sufficient energy, they will have more kinetic energy. They are moving around more. So they are more likely to collide, leading to an increase in the number of collisions and an increase in the energy of those collisions. Here we're going to use the example of sodium thiosulfate and hydrochloric acid for an investigation as to how the rate of reaction is affected by temperature. You may well be given a bit of paper or a bit of card with a cross on it at school, and you can put your conical flask on top of that, mix the solutions in the conical flask, and look at the solution changing. Over time, it will gradually go cloudy. So you can record the time that it takes for you to stop being able to see the crosses anymore. And I just want to have a little throwback to the really old way my videos used to look way back years ago. So the sodium thiosulfate and the hydrochloric acid will make sodium chloride, sulfur dioxide, and sulfur. The sulfur is the bit that you can see because it is a solid. It will precipitate out of the reaction and cause it to go cloudy. The time taken for a cross to disappear is a rough value. You can put numbers on it, time it, but if you want to improve this, we can use a colorimeter to give us proper, more accurate quantitative data. You can use a data logger with this as well, and it's beautiful. It'll just draw the graphs for you as you go along. There are some risks with this if we make it too hot. If you do it over 60 degrees, too much gas will be evolved and that will be poisonous and not good for you. We can draw some graphs of 1 over time versus the mean temperature. Put on a beautiful line of best fit. And the initial rate of reaction is proportional to 1 over time. Concentration and pressure also affect the rate of reaction, and we're going to do them together because they are very similar. An increase in concentration or pressure will lead to an increase in the rate of reaction. An increase in concentration is more particles in the same volume. An increase in pressure is the same number of particles in a smaller volume. Thus, the frequency of collisions will increase. Introducing a catalyst will have an effect on the rate of reaction. They increase the rate of reaction by providing an alternative pathway with a lower activation energy, causing there to be an increase in the number of particles that are able to react, and an increase in the number of successful collisions. If we look at our reaction profile, this is an uncatalyzed reaction and the activation energy that it takes for the reaction to happen. However, a catalyzed reaction will have a lower activation energy. Le Chatelier's principle and dynamic equilibrium is a great topic for questions. Le Chatelier's principle says that if an external condition is altered, the equilibrium will work to counter that change. It is important to remember that a dynamic equilibrium is not static. Both the forward and the backwards reactions are occurring at the same time, but not always at the same rate. The forward reaction is exothermic. Meaning if we increase the temperature, the equilibrium will shift to the left-hand side. To counteract this, the reverse reaction is endothermic, and this will increase to lower the temperature. This will give us a lower yield of ammonia. Conversely, what you think, increasing the temperature gives a lower yield of ammonia. But the industry conditions have to balance rates of reaction, which will increase, with the yield. The left-hand side has 4 moles, whereas the right-hand side has 2 moles. So an increase in pressure will favour the forward reaction. The right-hand side has fewer moles. Shifting the reaction this way will reduce the pressure. High pressure in industry might increase the yield, but maintaining that high pressure is expensive and can potentially be dangerous. If we change the concentrations, for example, increasing a reactant, it would shift the reaction this way to help counter it. Also, removing a product would shift it this way to counter it, but adding in a catalyst will have no effect, since both the forward and the reverse reaction will be sped up by this. Kc is the equilibrium constant for a homogeneous system. If we have a reaction here with the capital letters being our compounds and then the lowercase letters being their multiples, we can work out the equation for Kc by putting the product on top, and then these bits, the compounds, the substances, go in brackets, and then their multiples go outside of the brackets. The reactants go on the bottom. We use square brackets to show concentration. The units for Kc will vary, and the easiest, most simplest way to work this out without getting confused is just by writing it all out, not by trying to skip, guess, and do it in your head. Just take a little bit of extra time to write it out. Here is our equation for ammonia. So we are going to have ammonia on top with 2 outside. Down below, the reactants, we are going to have nitrogen and hydrogen, 3 lots of them. So that is our expression for Kc. If we're doing a calculation, we'll just take the numbers from the question and pop them in here. To work out the units, we just need to put the units in, not forgetting our multiples up here. And then to help you not get confused, write it out fully. So here we had 2 of them, so I've written out 2 of them. This one goes here. Here I've got 3 of them, so I'm going to write 1, 2, 3 out down here. And then it's algebra. We can cancel them out and see what we have left, giving us 1 over moles per decimeter cubed squared, giving us moles to minus 2 decimeters to 6. There are some things that will have no effect on Kc, that is concentration, pressure, or the presence of a catalyst. However, an increase in temperature will affect Kc. You will see an increase in Kc for endothermic reactions and a decrease in Kc for exothermic reactions. Single topic in chemistry that I have the most videos on. So if anything on this single slide is confusing, go and check out my individual videos on this. There are some rules for oxidation states that we have to obey to make everything simple. Uncombined elements will have an oxidation state of 0. The total oxidation states in a compound will add up to 0. The total oxidation states in an ion will add up to the charge on that ion. Group 1 elements will be +1. Group 2 will be +2. Hydrogen is +1 except in metal hydrides when it is -1. Oxygen is -2 except in peroxides or when combined with fluorine. Chlorine and bromine are -1 except in compounds with oxygen or fluorine. Here we have sulfuric acid. Hydrogen we know is +1 and we have 2 of those. +1 times 2 gives us +2 in total. Oxygen we know is 2. We have 4 of those. Minus 2 times 4 gives us minus 8 in total. This adds up to 0, meaning sulfur must be plus 6. For our carbon ion, we have an overall charge of minus 2. Oxygen we know is minus 2, and there are 3 of them. Minus 2 times 3 is minus 6. Overall, we need to get to minus 2. So what plus minus 6 makes minus 2? Well, that is plus 4 for the carbon. In a metal hydride, we know sodium in group 1 will be plus 1. This is an exception for hydrogen, so hydrogen will be minus 1, giving us 0 overall. Hydrogen peroxide, H2O2. Hydrogen is going to be plus 1, and we have 2 of those. So plus 1 times 2 gives us plus 2. This needs to be 0 overall, which means that oxygen needs to, in total, add up to minus 2, meaning they need to be minus 1 each. Minus 1 times 2 gives us minus 2. We can look at the names and the Roman numerals and things to work out what they are. Copper 2 means it has a 2 plus ion. Nitrate 5 means the nitrogen is going to be plus 5. And from copper 2 nitrate 5, we can work out the formula of this compound. Really useful if you have iron compounds. We know the nitrate is going to be minus 1. Oxygen is minus 2. We have 3 of those, so that gives us minus 6. We know nitrate is plus 5, giving us NO3 minus. Copper is plus 2, so we need 2 nitrate ions to go with the copper. When we are looking at redox reactions, we can use oil-rig to help us remember what things are. Oxidation is loss of electrons. Reduction is gain of electrons. If we have a decrease in the oxidation number, it has gained electrons and been reduced. An increase in the oxidation state, we have lost electrons and been oxidized. So chlorine on its own will have an oxidation state of 0. Sodium group 1 metal will be plus 1, oxygen minus 2, hydrogen plus 1. These are from our rules. Sodium plus 1, chlorine minus 1. We can see chlorine started off with 0 and went to minus 1 and plus 1. So here we have seen a decrease in the oxidation state, showing that it has gained electrons and been reduced. Here we see an increase in the oxidation state. This has lost electrons and been oxidized. This type of reaction, where the same thing is oxidized and reduced in a single reaction, is a disproportionation reaction, and that's one of my favourite words. Sometimes with redox reactions, we know the start point and we know the end point, and we can work out the half equation that has happened. Again, there are some rules for us to follow. Any oxygens are balanced with water, hydrogens are balanced with hydrogen ions, and any charges that are uneven are balanced with electrons. Here we have a reaction that we know occurs, but it is not balanced. Adding in 4 waters will balance out the oxygens, but now the hydrogens are not balanced. So we need to add in 8 hydrogen ions and then add in electrons to balance the charges. The other half of this reaction, we need to start by balancing the hydrogens because the oxygens are already charged, and then add in electrons to balance out the charge. Then we can add these two together. Looking at the electrons, there are not the same number of electrons, and we can't just have electrons disappear. So we need to change the bottom reaction, multiplying it by 5, so there's 10 electrons, and the top one by 2, so there are 10 electrons. So I'm just going to write it out here with this reaction being multiplied by 2. And with the bottom reaction being multiplied by 5, we can now use algebra to start cancelling things out. 10 electrons on either side don't need to be written down, they can cancel it out. And so can some of the hydrogens. We can then write this as a complete overall reaction. This may seem very complicated, but with a bit of practice, you'll get the hang of it, no problem. There is structure and order to the periodic table, and understanding it will help you immensely. It is arranged by increasing atomic number, not by mass. For example, we have argon here and krypton here. Argon has 18 protons and a mass of 40, whereas potassium, which comes after it in the periodic table, has 19 protons and a mass of 39, a lower mass which might make it seem like it's in the wrong order, but it is arranged by atomic number. Everything within a group will have similar chemical properties. They have the same number of electrons on the outer shell. Periods will go across the periodic table. They will show a repeating trend. This is periodicity. They will have the same number of electron shells, but an increasing number of electrons on the outer shell. The structure can also help you remember how many electrons go in each shell. For example, in the first period, period 1, there are 2 elements, so there are 2 electrons. In the second period, there are 8 electrons and 8 elements. The same in the third period, there are 8 elements in that period and there are 8 electrons in that shell. The periodic table can be divided up into blocks. The S block, the D block, the P block, and the F block. Period 3 goes across here on the periodic table. This is an example period, and similar trends are seen in other periods, for example, period 2 just above it. As we move across the group, we're going to see a decrease in atomic radius. As the number of protons increases, so does the positive charge in the nucleus, further attracting the outermost electrons inwards. If we look at the trends in first ionization energy, there will be a decrease between magnesium and aluminium. This is as the S shell gets full and we start filling up p orbitals. There is also another drop between groups 5 and 6, between phosphor and sulfur, as pairing starts. Repulsion increases slightly here. Sodium, magnesium and aluminium will have strong bonds, leading to high melting and boiling points. Silicon also has strong covalent bonds. It is a drying structure. It will have high melting and boiling points. Chlorine, sulfur and phosphorus are simple covalents, so they will have weak intermolecular bonds, leading to low boiling points. And argon is monoatomic, very low boiling points. For group 2, we are looking at the ones going down on the left-hand side. These are the alkaline earth metals, and they will have 2 electrons in their outer shells. This makes them all very reactive. As you go down the group, the atomic radius increases. This is due to the increase in the number of electron shells. The melting point will decrease. This is due to the increased distance between the nucleus and the outermost electrons, reducing the electrostatic attractions between atoms. There is a decrease in the first ionization energy. As the number of shells increases, the shielding increases. Reactivity increases as you move down the group, as outermost electrons are more easily lost. If we have a group 2 metal and water, we will get a group 2 metal hydroxide and hydrogen. A group 2 metal plus oxygen will give us a metal oxide. Group 2 hydroxides become more soluble as we go down the group. Magnesium hydroxide is very sparingly soluble, almost insoluble, and it's used to treat stomach acid. Calcium hydroxide is used to neutralize acidic soils. Calcium oxide and calcium carbonate is used to remove sulfur dioxide from flue gases. Magnesium can be used to extract titanium. Titanium needs to be very pure, so it can't be extracted just by carbon. It is a batch process, making it very expensive. It also uses large amounts of electricity. Group 2 sulfates get less soluble as you move down the group. Barium sulfate is insoluble. It is given to patients when they are needed to have an X-ray of soft internal organs. The barium means that when you have an X-ray, you can actually see the structure of these organs. When we are testing for sulfate ions, we need something with sulfate in, hydrochloric acid and barium chloride. Acidified barium chloride with hydrochloric acid can be used to test for sulfate ions. It will give a very nice positive result of going white. A white precipitate will be formed. If you are doing a single test tube set of reactions and the order of tests is important, the chloride ions in barium chloride will give you a false positive on a test for halide ions. So the order of these reactions is important. Group 7 or Group 17 sits over on the right-hand side, and these are the halogens. Fluorine gas is a highly reactive pale yellow gas. Chlorine gas is a poisonous pale green gas. Bromine liquid will give off poisonous fumes. It is also used to test for alkenes. Iodine is a grey solid that sublimes. Sublimes means something goes from a solid straight to a gas, bypassing the liquid phase, to give us a purple gas. As you move down the group, the electronegativity decreases. The increasing number of shells and increases the atomic radius, reducing the ability of the nucleus to attract the electrons. As you move down the group, the melting and the boiling points also increase. The increasing number of electrons increases the strength of the intermolecular forces. We can talk about displacement reactions involving halogens. More reactive halogens can act as stronger oxidizing agents. And the stronger oxidizing agents will replace weaker oxidizing agents in a reaction. When this happens, you are likely to see a colour change. For example, if we have chlorine added with bromide ions, we're going to get chloride ions out and bromine. We're going to go from a pale yellow solution to a solution of bromine, which is an orange-brown colour, and chloride ions. When we are talking about the halogens, we can see a lot of trends in their reactions. They have an increasing ability as reducing agents as we move down the group. Sulfuric acid added to a sodium halide will generally give us a hydrogen halide gas, because here the halide ions are acting as a base, and the sulfuric acid is reduced. Fluorine and chloride are not strong enough reducing agents, so here you will only see the acid-base reactions occurring. With sodium bromide, it is a moderately strong reducing agent, so you will see the acid-base reaction as well as the redox reaction taking place. Iodide ions are a strong reducing agent, so here is our overall equation. But from this, there are lots of other reactions going on, not only acid-base reactions, but redox reactions as well, leading to a wide range of products, not just the hydrogen iodide, but iodine, sulfur dioxide, sulfur, water, and hydrogen sulfide. With all of these reactions, what you will get out is a white steamy fumes of the hydrogen halide gas, which will turn blue litmus paper red. When we are testing for halide ions, you are going to need a solution of that halide ion. We are going to add to it silver nitrate and nitric acid. We will then see a faintly coloured precipitate, a solid coming out. Silver chloride will give us a white precipitate. Silver bromide will give us a cream precipitate. And silver iodide will give us a yellow precipitate. If you look at the video, you will see that the colours are very, very close to each other. If you are doing this in a lab as a practical, it is a really good idea to have a standard set you can refer to, because telling the difference between white and cream when you've got no reference is really, really hard. The nitric acid is there to remove any carbonate ions. They will react and turn into carbon dioxide, since the silver carbonate will give a false positive here. If we add dilute ammonia to silver chloride, then we will get a complex ion. This is a colourless complex ion, so the white colour will disappear. The same will happen to silver bromide upon the addition of concentrated ammonia, whereas silver iodide does not react with ammonia. We can start by looking at the reaction of chlorine with water. Chlorine in a reversible reaction with water will give us hydrochloric acid and chloric acid. Chlorine with an oxidation state of 0 will have an oxidation state of -1 in hydrochloric acid. This is a decrease in the oxidation state. It has gained electrons and been reduced. We can also see chlorine having an oxidation state of 0 and going to +1. This is an increase in oxidation state. It has lost electrons and been oxidized. Where the same thing has been reduced and oxidized in a reaction, this is called a disproportionation reaction. HClO is chloric 1 acid. This is what we use in swimming pools to kill bacteria. It is also used to treat drinking water. Be dangerous, and this leads to a balance and potentially a controversy. However, on the balance of things, the benefits of killing bacteria to provide safe drinking water for people outweigh any minor potential tiny risk of there being too much chlorine in the water. Chlorine can also react with cold dilute alkali. A reaction with sodium hydroxide will give us sodium chloride and chloric acid and water. Again, this is the disproportionation reaction. ClO- is the chlorate 1 ion. Sodium chlorate is bleach. We are just going to take a tiny segue here to talk about naming things and ion. This is sodium chlorate, sodium 1 chlorate, because we know in here the oxidation state of chlorine is 1, but this is also sodium chlorate. However, sodium here has an oxidation state of 1. We know oxygen is -2, and there are 3 of them, giving us -6 in total. The whole thing is 0, so chlorine must be +5. So this is sodium chlorate 5. This is one big example where using the Roman numerals is important. If you see them, write them down and pay attention to them. A favourite practical in A-Level Chemistry and a favourite exam question is being given a mystery solution or a mystery white powder and being asked to use the knowledge of tests to work out what it is. So here is a summary of all the test tube tests for cations and anions. There are also the flame tests we can add on to this as well. When you are testing for halide ions, we add nitric acid and silver nitrate. Chloride ions will give us a white precipitate. Bromide ions will give us a cream precipitate. Iodide ions will give us a yellow precipitate. They can go colourless if we add dilute or concentrated ammonia. To test for sulfate ions, we will add barium chloride and dilute hydrochloric acid. A positive result will be a white precipitate. For carbonate ions, we will add hydrochloric acid. We will see a gas given off. This will be carbon dioxide gas. To confirm it's carbon dioxide gas, we need to see the gas turning lime water cloudy. Hydroxide ions can be added to ammonium chloride, and it will start to be very smelly, leading on to the inverse test for ammonium ions. And we will get smelly ammonia released. To confirm that it is ammonia, what we will be looking for is turning damp red litmus paper blue. To test for group 2 ions, we're going to be adding 2 different things: sodium hydroxide and sulfuric acid, both dilute and concentrated. For barium, either the dilute or concentrated sodium hydroxide will give us a colourless solution. Either dilute or concentrated sulfuric acid will give us a white precipitate. For calcium ions, the addition of either dilute or concentrated sulfuric acid or sodium hydroxide will give us a slight white precipitate. Magnesium ions with dilute sodium hydroxide will give us a slight white precipitate, whereas concentrated sodium hydroxide will give us a white precipitate. Dilute sulfuric acid will give a slight white precipitate, and concentrated sulfuric acid will give us a colourless solution. Strontium and either dilute or concentrated sodium hydroxide will give a slight white precipitate, whereas the addition of dilute or concentrated sulfuric acid will give a white precipitate. If you are asked to do all of these in a single test tube, then the order of reactions does matter. For example, here we are adding barium chloride. So if you want to test for sulfate ions and halide ions in a single sample in a single test tube, if you do this one first, you are adding in chloride ions and you will get a false positive for halide ions. The order does matter. Organic chemistry nomenclature is very important because it tells you what an exam question is asking you for. The empirical formula is the simplest whole number ratio of each element within a compound. The molecular formula is the real number of atoms of each individual element in a compound. The general formula will be the formula that covers a homologous series. The structural formula is the minimum level of detail you need to draw something, so CH3, CH2, CH3. The displayed formula will show all of the bonds, whereas the skeletal formula will not show any carbons or any hydrogens, just skeletons and other functional groups. Lots of the words we use in organic chemistry might be new to you, so it's worth spending a bit of time going over them. A homologous series is a group of compounds that has the same functional group, but each one will have a different length carbon chain. A functional group is the group of atoms within a compound that give the compound its properties. An alkyl group will be potentially a side chain with the formula CnH2n+1. An aliphatic compound will be straight chains branched on non-aromatic rings, based around hydrogen and carbon. Alicyclic compounds will have non-aromatic rings, whereas aromatic compounds will contain benzene rings. A saturated compound will only have single bonds between carbons, whereas unsaturated compounds will have double bond between carbons. An easy way to remember this is that when we have saturated things, they are alkanes and there is one E in there, so they are single bonds. And unsaturated will be alkenes. There are two E's in there. That is a double bond. It's crude, but it works. When drawing, you can draw the displayed, the skeletal, or the structural formula. If one of these is mentioned in a question, please give the examiner what they are looking for. The displayed formula will show all of the bonds. Here we can see each of the carbons, and these will become points on the skeletal formula, and we are going to draw in the backbone between these carbons. No hydrogens, and then we need to draw on the functional group as well. For our structural formula, we take it bit by bit. Here we have a CH3, here is a CH2, here is another CH2, and then an OH. This is propan-1-ol. Here is another example, again picking out the carbons as the turning points in our skeletal formula, drawing those points, those dots on as our backbone, and connecting them up. We have a CH3, a CH, and a CH2, and this is propane. Slightly more complicated one now. Again, we are going to start by using our carbons as our points, as our backbone of our skeletal formula, drawing on the backbone and the functional group. For the structural formula, we have a CH3, CH2, CH2, and a COOH, giving us butanoic acid. When we are naming things in organic chemistry, we use the IUPAC rules. I have a large number of very long videos going over lots and lots and lots of examples of naming things in organic chemistry. This, remember, is just a brief summary for your revision. If you're confused by any of these bits, go and watch one of the longer videos. These are the rules we follow whenever we are naming something in organic chemistry. Find the longest carbon chain. This is not always a straight chain. This is the backbone for the naming. Identify all of the side branches. Circle and identify all of the functional groups. Number the chain so the branch with the highest priority functional group has the lowest number. We're going to use di-tri for more than one of a branch of the same type. Branches always go in alphabetical order. There are commas in between numbers. Hyphens separate numbers from letters. And there are no gaps between names of things. We are going to use these rules to name things, starting with the basics, alkanes. You're going to see me use this template a lot. It is super helpful for organic chemistry, and you can download it for free from my website. Names have different parts to them: first names, surnames, prefixes, and suffixes. The prefix comes from the number of carbons, so 1 is meth, eth, prop, 4 is bute, 5 is pent, 6 is hex. So here is something that I've drawn. The first thing we do is to identify the longest carbon chain, highlighted here in green, and then count the number of carbons in that chain. So 4, it is going to have a bute prefix. Here is a side branch. There's only one of them. This is a methyl side branch. Putting it all together, this will be methyl butane. The ane tells us it has single bonds in it. Here's something else a little bit more complicated. Start in the same way and find the longest carbon chain, count things. So we know that we have 6 carbons, giving us hex as the prefix, and ane because it's an alkane. Here are our 2 branches. One of them has 1 carbon in and one of them has 2 carbons in, giving us a methyl and an ethyl. We need to start numbering from over here because that is where we are going to get the lowest numbers possible. So this gives us 3 ethyl and 2 methyl. we can now start to put the name together. Because they need to be in alphabetical order, not in number order, we have 3-ethyl, 2-methyl hexane. Now, with practice, all of these skills will come very naturally to you. So we can start to look at horrible looking things and name them. The first thing we need to do, as always, is highlight the longest carbon chain, and here we can see it's not straight at all. Please feel free to use colour pencils and highlighters in this sort of question. 7 carbons in the chain gives us heptane. Now we need to find all those branches. There are 4 different branches on this one. They all have 1 carbon in, so they are all methyls. Now we need to look at the numbering, so we end up with the lowest possible numbering. I'm just going to draw it on from both directions, trial and error, to see which way will give me the lowest possible numbers. And we can see this is an example where it actually doesn't matter which way round we get it. It's either going to be 3, 4, 4, 5. Now we have all that information, we can start to build the name up. Now this is one word, even if I can't fit it all on one line. We have 4 methyl groups, so it's 3, 4, 4, 5 dash tetramethyl heptane. One word, which they did manage to fit on one line. Different functional groups will change the suffix of the word. So we have ANE for alkanes. An alkene will have a double bond in it somewhere, and it has an ENE, but-2-ene here. An alcohol will have an OH functional group. This one, 4 carbons, butan, 2-ol. Alkanes with halogen attached to them in front, so this is 2-chlorobutane. Aldehydes will have this functional group on the end, and this is butanal. An isomer of theirs, ketones, will have the functional group in the middle, and this is butanone. Carboxylic acids have their functional group on the end, and this is butanoic acid. Esters will have their functional group in the middle, and we have 4 on each side, so this is butyl butanoate. There is a priority list of functional groups, starting with carboxylic acids, moving down to aldehydes, ketones, alcohols, alkenes, and halogens. So in a compound that has more than one functional group, this is the order that we need to go through when we are naming things. Here we have an alkene, we have a methyl, and we have some halogens. Using our rules exactly the same way that we have before, the first thing we need to do is to find the longest carbon-carbon chain. 1, 2, 3, 4, 5, 6. So this is hex. We have a methyl group, a chloro group, a bromo group, and trial and error numbering to see which ones give the highest priority group the lowest numbers. Do it from both sides. And we can see that the blue numbering will give the double bond the highest priority group, the lowest numbering. So this is what we need to go with, this blue numbering here. Now the chances of me fitting this name on one line are slim, but remember this is all one long name. Putting it all together, we have branches going in alphabetical, not numerical order. So B becomes 4C. So we have 5 bromo, 4 chloro, 5 methyl, hex, 2-ene. Another example that looks horrible, but once you follow the rules is absolutely fine. We are going to start to be drawing lots of reaction mechanisms. It is important you understand what all of the different things mean. If you want to get full marks on an exam question, you need to have really careful drawing of arrows. A dot is an unpaired electron. A fishhook arrow, a half arrow, shows the movement of 1 electron. A double-headed arrow will show the movement of 2 electrons. For example, in homolytic fission, we will get electrons moving from the middle, 1 to each chlorine, giving us 2 chlorine radicals. In heterolytic fission, and remember, homo is the same, so both the products at the end will be the same. Hetero is different, so the products at the end will be different. Here we have both electrons going in one direction, so we will get a plus ion and a minus ion. Here we can see the breaking of a covalent bond, with the arrow starting at the bond and then the electrons going somewhere else. You always have to be very careful with where your arrows start and where they actually end up. They start here and they will go here. When you're writing on charges, make sure they are next to the thing they are actually on. And when you're doing formation of bond, the curly arrow starts at the electron that will be in the bond. Structural isomers will have the same formula, the same number of each element of each atom, but will have a different structure. Here we have some examples. Here is 4 carbons in a straight chain, and here is 4 carbons but with a branch. So in a straight chain we have butane, but when it is branched we have methyl propane. They both have a formula C4H10, but as you can see from the molemods and as you can see from the displayed formula, they are different arrangements. These are chain isomers and they will have different physical properties. For example, branching will give different boiling points. Here we have propanol, but the alcohol group is in a different position. We have propan 1-ol and we have propan 2-ol. One of them will have the OH group on the end, whereas the other has the OH group in the middle. These are primary and secondary alcohols. These are position isomers. They will have the same functional group but in a different place. Here we have an oxygen added in, but we can see that here it is on the end, whereas in the isomer it's not on the end, it's in the middle. This gives us a different functional group. These are functional group isomers because butanal is an aldehyde and butanone is a ketone. The same formula, but the different position in this place of the double bonded oxygen. Stereoisomers are also called EZ isomers. Here we have but2ene with the double bond in the middle, but you can see they look different. These are not exactly the same. Even though the displayed formula would indicate to you that they are, we can see these are going up and down and these are going up. They have a different arrangement in space. This is because there is no free rotation around the double bond. And this only works if there are different groups. Here they are drawn out a little bit clearer. So you can see here the CH3 group are on opposite sides, and here the CH3 group are on the same side. Where they are on opposite sides, this gives us the E isomer, so this is E-but2ene, and when they are on the same side, it is the Z isomer, so this gives us Z-but2ene. As a point, but1ene doesn't show EZ isomerism because on one of the carbons on the double bond, these two groups are the same. So it doesn't matter which way up or round it goes, it will be the same. These are the priority rules for deciding whether something is an E isomer or a Z isomer. Your E isomers will have priority groups on different sides of the double bond. Your Z isomers will have priority groups on the same or the same, side of the double bond. Priority is determined by the atomic number. Here are some lovely examples. We have 2 chlorines on a butene, so giving us 2,3-dichlorobutene. Chlorine at 17 has a higher atomic number than carbon, so it has the higher priority. Here are the chlorines highlighted, and you can see in this one they are on the same side. So this is the Z isomer and this one is the E isomer. Isomers can differ in polarity because the E isomer is symmetrical. It has polar bits on both sides, so it cancels each other out overall and is not polar. Whereas here, the Z isomer is polar because the polar bits are both on the same side, giving it a polarity. They can also differ in their boiling points due to the differences in the intermolecular forces made. Fractional distillation is a way of separating out crude oil. And crude oil is a mixture of different length hydrocarbons. And a hydrocarbon is something that only has hydrogen and carbon in it. The length will influence the properties. So longer chains will have an increasing number of van der Waals forces, holding them together. And the more intermolecular forces, the higher the energy needed to separate them, thus the higher the boiling point. Very briefly, the oil is heated. It goes into the column and it separates out at different boiling or condensing points, thus separating them by chain length, with short ones at the top and long ones at the bottom. Crude oil is a mixture of different length hydrocarbon chains. The short ones are very useful and are used a lot, but not enough of them is produced from fractional distillation. The long ones are not used very much and lots of them are left over at the end. Cracking is a way of turning long chain hydrocarbons into shorter chain hydrocarbons, alkanes and alkenes. When we are talking about alkanes and alkenes, alkanes are saturated because they have all single bonds, and alkenes are unsaturated because they will have double bonds. We can have catalytic cracking, which uses a zeolite catalyst. It's done at 450 degrees C and a moderate pressure just above 1 atmosphere. This is more efficient as it uses less energy, lower temperatures and lower pressures. It will give us branched and cyclic alkanes and aromatics such as benzene. Thermal cracking is done at higher temperatures, 400 to 900 degrees C, a high pressure of 7,000 kilopascals, and will give us lots of double bonded alkenes. When we are combusting alkanes, we are using them as a fuel, and they have a wide range of uses as a fuel. Gas for heating, an example in your Bunsen burners, petrol in vehicles, kerosene, for example in airplanes, even through to the simple wax you have in candles. Complete combustion is done with lots and excess of oxygen. The alkane plus oxygen will give us carbon dioxide and water. Incomplete combustion is in a limited supply of oxygen, and the range of products come out of this are much wider and variable depending on the conditions. Again, we will get carbon dioxide and water. In addition, we will get carbon monoxide and carbon. There is a lot of pollution from combustion. Carbon dioxide contributes to climate change, as does water vapour, as they are both greenhouse gases. Carbon monoxide is a toxic gas that can lead to death. Carbon is soot that can lead to global dimming and atmosphere pollution, leading to breathing difficulties. Sulfur dioxide can lead to acid rain. And various nitrous oxides can be toxic gases and lead to acid rain. Unburnt hydrocarbons are another pollutant. In industry, sulfur dioxide can be removed from flue gases by reacting it with calcium oxide, which will neutralise it. In vehicles, can remove carbon monoxide and nitrogen oxides, turning them into nitrogen gas and carbon dioxide. Still pollutants, but not as bad. And they can take the unburnt hydrocarbons and react them with nitrogen oxides, giving us safer products. The catalytic converter will have a honeycomb structure. It will have platinum, palladium, and rhodium as a catalyst. The chlorination of alkanes can be looked at by adding chlorine to methane. For this, UV light is needed. However, beyond this reaction here, it is actually much more complicated than it seems. We're going to look at the process of free radical substitution. Step 1 is the initiation step, where with UV light, chlorine Cl2 will produce 2 chlorine radicals with this free unpaired electron. This is the process of homolytic fission, where one electron from the bond will go evenly to each chlorine. Step 2 is a propagation reaction. Methane will react with those chlorine radicals to give a CH3 radical, which will then go on to the next step of the reaction. Notice here how I've drawn the radical on the carbon because that's where the electron actually is. This CH3 radical will react with Cl2 to give us chloromethane and then give us back our chlorine radical. This is why it's a propagation reaction, because we start and end with the same thing. The electron from the chlorine radical will go in to this bond here, and the electron here will move over. Then this radical will then go and attack this bond, and the electron will move over, giving us back another radical. Step 3 is termination of this, where we will get 2 radicals reacting together to form something that is not a radical. These can be a range of different termination steps, following on from a range of different propagation steps. This one here is the one that is more likely to be shown. This can then go back to the beginning in a chain reaction, whereas this is a minor waste product. If we look at our original equation, the actual products are the ones that are produced in the propagation step, and our reactants are used in the initiation and in propagation. It is important that you learn nucleophilic substitution reaction mechanisms carefully and you can draw them accurately in an exam. This is an example that can be applied to lots of other situations. Nucleophiles are electron pair donors, and the ones you need to know about are hydroxide, ammonia, and cyanide. And for substitution, we are swapping one thing for another thing. Here we have chloroethane and our nucleophile. It is important that you draw on your charges. These are our partial charges, and then the arrow will start at the electron. It will start at the charge that is attacking the bond, and it will end exactly where it is going, to that positive, delta positive carbon. And then the electrons from the bond will move over to the halogen. Then we will have a swapping, a substitution, as that nucleophile pops itself in there. There are slightly more complicated examples. If we have ammonia as the nucleophile, again, our arrow needs to start where it starts and end where it actually ends. Accuracy is so important when you are drawing these, otherwise you will not get the marks. And this time we have an intermediate, which is attacked by another nucleophile, with the electrons from the right-hand side moving over, and then we will have 2 products in the end, a chloride ion and an ammonium ion. The rate of these reactions depends on how strong the bonds are. The carbon-fluorine bond will be the strongest, whereas the chlorine-iodine bond will be the weakest, meaning any reaction that is involving carbon-fluorine will be slow, whereas any reaction involving carbon-iodine will be fast. Elimination reactions can happen with hydroxide. If we have a metal hydroxide and alcohol solution, it will be an elimination reaction, whereas a metal hydroxide and aqueous solution, we will get a substitution reaction. Here we have bromoethane and our hydroxide ion. It is really important when we are drawing mechanisms that your arrows start and end in the correct place. Our arrow starts from the negative charge and goes to the hydrogen. From the middle bond connecting the hydrogen and the carbon, the electron will then move to the bond connecting the carbon and the carbon. And an electron will move from the covalent bond over to the bromine. This will create a double bond and will release a bromide ion and water. Hydrogen is lost from the carbon adjacent to the carbon that has the halogen. We can see this reaction happen when we have potassium hydroxide in alcohol. The depletion of ozone has an important set of reactions in it. Chlorofluorocarbons, CFCs, are very, very useful. They are useful as solvents in refrigeration and aerosols. They were widely used but not disposed of properly or safely. Carbon, we have carbon-fluorine bonds, which are short and very strong, and we have carbon-chlorine bonds, which are longer and weaker. The carbon-fluorine bonds are not affected by UVs, which is why scientists have now shifted towards using hydrofluorocarbons instead of chlorofluorocarbons, as they are safer. This is a free radical reaction. We will start with initiation using UV as an essential. This will give us our chlorine radicals. The chlorine radicals can then go on to react with ozone, O3, to give us another radical and oxygen gas. These radicals then keep the reaction going, reacting again with ozone to remake this propagation, remake the chlorine radical, and give us more oxygen gas. The reaction will eventually end at some point with two radicals reacting with each other. And the overall reaction for this is 2 lots of ozone will be turned into 3 lots of oxygen gas. Ozone in the upper atmosphere is important for protecting us from UV radiation. Breakdown of ozones by CFCs contributes to the hole in the ozone layer. Bonding and reactivity of alkenes is fascinating. They are unsaturated. They will have a double bond, so an alkene has that double E in there to help you remember. The position of the double bond doesn't always stay the same. Here we have butene, but 2 different versions of butene, depending on where the carbon-carbon double bond is. Around carbons in the double bond, we will have a planar geometry, whereas around other carbons in the compound, we will have a tetrahedral geometry. These 2 examples here give us but1ene and but2ene. This double bond in the middle is an area of high electron density. Electrophilic addition reactions are going to happen in this type of reaction because of the area of high electron density. In a double bond, we have 2 types of bond. We have sigma bonds and we have pi bonds. Lots of electrons all in one place. There are a few mechanisms, electrophilic addition reaction mechanisms of alkenes that you need to know and be able to draw properly. The first one is the addition of hydrogen bromide. Hydrogen bromide is polar, so the electron-rich double bond will be attracted to the delta positive, which will move the electron in the covalent bond down to the bromine. This will produce a carbocation intermediate, and the negative bromide ion will be attracted to the positive carbon, and the bromine will be added on. Electrophilic addition reactions with sulfuric acid will look very similar, with the electron-dense region attacking the delta positive hydrogen and the electron moving over to the oxygen, giving us a carbocation as an intermediate. The negative oxygen can then attack the positive carbon, giving us yet another intermediate at the end of stage 1, at the end of electrophilic addition. Stage 2 is a hydrolysis reaction with water, whereas we will get a hydroxide ion added on and sulfuric acid remade as the catalyst. For stage 1, you need cold concentrated sulfuric acid, and for stage 2, you need warm and you need to add in water. If you wanted to add on bromine, it will look very similar to our first reaction over here, except you will get bromine in both positions. You will see an orange to colourless change, and this is the test for alkenes. Working out the major and minor products in a reaction is also known as Markovnikov's rule. Here we have an asymmetrical alkene which we're going to add hydrogen bromide to. Now where the hydrogen goes and where the bromine goes, we don't yet know. It can go onto either carbon. Depending on the position of the bromine, we will get different compounds. Either 1-bromobutane or 2-bromobutane, and if you're in industry and you want to make a particular thing, then this is important. Here we have our hydrogen bromide, which is a polar molecule. The electron-dense region of the double bond will be attracted to the delta positive hydrogen, and the electrons in the bond will move down to the bromine. A hydrogen will be added on and we will get a carbocation. The negative bromide ion will be attracted to the positive charge on the carbocation, added to the carbon with the fewest hydrogens on it. So this will be the minor product. This carbon here has fewer carbons than this carbon here, so the electrophile will preferentially add on to this carbon, making 2-bromobutane the major product. The major products will come from the more stable carbocation. In terms of stability, primary are the weakest, whereas tertiary carbocations are the most stable. Here we have a secondary carbocation, whereas this one is a primary carbocation. Addition polymers can occur with alkenes. Here we have chloroethene, and to draw it as a polymer we need to extend the bonds outside of the square brackets, put on square brackets and put an N on there to show it's a repeating unit. This will then become polychloroethene. It is very long to draw out, which is why we generally don't draw the whole thing, but it will have multiple repeating units of chloroethene. Polychloroethene is also known as PVC, and it is incredibly useful. It's waterproof, it's an insulator, and it's very unreactive. The very strong intermolecular bonds prevent chains from moving over each other, making it very, very strong. A plasticizer, something to break those strong intermolecular bonds to get in the way, can be added to help chains move over each other, so that PVC can be used for clothing and wires. Unplasticized PVC, UPVC, can be used for window frames, something that needs a very strong plastic. The naming of alcohols is very similar to alkanes. Here we have 3 different alcohols with the functional group in a different place. This is butan 2-ol. It is numbered so that the functional group has the lowest possible number. If we use the green numbers, it would be butan 3-ol, which is not correct. This is butan 1-ol with the functional group on the end. The last one has a 2-methyl group and the functional group on the 2-carbon, making it 2-methyl butan 2-ol. Butan 1-ol is a primary alcohol, butan 2-ol is a secondary alcohol, and 2-methyl butan 2-ol is a tertiary alcohol. It is not the names that determines whether it's primary, secondary, or tertiary, but what is attached to the carbon that the functional group, the OH group, is attached to. How many carbons and how many hydrogens it's attached to. If we have more than one alcohol functional group, then we can call it a triol or a diol. There is a tetrahedral geometry around the carbons, but there is a bent geometry, as in water, around the OH functional group. Remember, this oxygen is going to have lone pairs on it. And the oxygen in the hydrogen in this are going to have a dipole established. This means between alcohols we are going to get intermolecular bonding, leading to the properties of low volatility, low boiling points, and then being good solvents. There are 2 methods for the production of alcohol. The hydration of ethene. Here we have ethene with the electron-dense region around the double bond attacking the hydrogen ion, giving us a carbocation. Water or steam, the lone pair will then be attracted to that carbocation. giving us an intermediate with a positive charge. The electron from the covalent bond will break that, giving us an alcohol and regenerating the hydrogen ion. The hydrogen ion from the phosphoric acid catalyst, 300 degrees centigrade, so very hot, and 70 atmospheres, high pressure. Steam will also be needed to be added. The advantages for this are that it is fast, it is a continuous process, and we will get a very pure product at the end. The disadvantages, however, is that the ethane comes from crude oil. It is a non-renewable resource, it will run out, and is in a high demand for other things. Due to the high temperatures and the high pressures, this has a high energy consumption, making it expensive, limiting its use. The second method is the fermentation of sugars. Glucose will be fermented to ethanol and carbon dioxide. We will need yeast for this, and this is an anaerobic respiration reaction. It will need a moderately low temperature for the yeast to be able to work. Too hot and yeast just doesn't work. The advantage is that sugar is a renewable resource. It is a pretty low-tech solution, so lots of developing countries can use it with low startup costs and low startup needs. The disadvantages is that it's a batch process. This makes it very slow and laborious. It also gives an impure product and needs to be an additional step of distillation afterwards. Ethanol can be used as a biofuel. The ethanol is produced via fermentation. Growing the sugarcane will remove carbon dioxide from the atmosphere during photosynthesis. The glucose from photosynthesis will then be fermented, and the alcohol from fermentation will be burnt in combustion as a fuel. 6 carbon dioxides are removed from the atmosphere in photosynthesis, 2 are released during fermentation, and 4 during combustion, making this process carbon neutral as no net carbon dioxide is added to the atmosphere in this set of equations. However, this doesn't take into account the energy used to grow the crops, the irrigation, the farm machinery, and the distillation that's needed to purify it afterwards. If the electricity, the energy for this, comes from a fossil fuel power station, then this process actually does add carbon dioxide to the atmosphere. There are also a few ethical issues associated with this. The sugarcane that is used as a biofuel could be used to feed hungry people. A large amount of land is used for this. This land could be used to grow other crops, which could be used to feed people. And the habitats, the destruction of habitats of what was there before, is a massive problem. When we are looking at oxidation of alcohols, you need to be aware of the differences between primary, secondary, and tertiary. Here we have primary alcohol, and we are going to be using an oxidizing agent, which we show by square brackets with an O in it. This is going to give us ethanal at the end. This is going to give us an aldehyde. This is after gentle heating. The aldehyde can then be further oxidized to give us a carboxylic acid. This requires more continuous, vigorous heating. This happens under reflux, the further oxidation to give us the carboxylic acid. Secondary alcohols can be oxidized to give us ketones, which have a similar but different position of the functional group. Tertiary alcohols cannot be oxidized. It is important to remember the differences in what can and can't be oxidized and how far they can be oxidized. The oxidizing agent that is used is acidified potassium dichromate. We will start off with the chromate 6 ion being orange, and after the oxidation reaction has happened, the chromate 3 ion is going to be green, so we will see a colour change in here. However, this is a reaction you've probably seen in real life, and you'll notice these are not nice colours, it's a pretty dirty green we get at the end. Distillation will turn a primary alcohol into an aldehyde. and a secondary alcohol into a ketone. Reflux is more vigorous, continuous heating, and it will turn a primary alcohol into a carboxylic acid. It will also turn any aldehyde into a carboxylic acid. Tollens reagent can be used to a silver mirror test for an aldehyde. Tollens is going to be made from ammonia and silver nitrate, giving us a complex ion. We will then have the aldehyde reacting with the silver ions, producing silver. This will give us the silver mirror on the side of a test tube. This is an incredibly temperamental reaction. So if you didn't manage to get this to work in the lab, do not worry. Lots of interfering ions from tap water will stop this working. You need to heat this very gently to get it to work. Saline solution can also be used to test for an aldehyde. We will get blue copper ions precipitating a red precipitate. Again, not always the cleanest of looking reactions here, giving us copper oxide. At the end, we will have a carboxylic acid produced and the copper oxide. Elimination reactions of alcohol are also known as dehydration reactions because we are going to be losing water. We are going to need a concentrated acid for this, and it needs to be done under reflux. Here we have our alcohol. The lone pairs on oxygen are going to be attracted to the positive hydrogen ion, giving us a positively charged intermediate. The electrons in the covalent bond are going to move, breaking that bond, giving us a carbocation, and the electrons in one of the covalent bonds to a hydrogen will break, giving us a double bond. This dark purple example has given us but-2-ene, but it is not always necessarily the same bond that breaks. This example here, the slightly lighter purple bond could break, and then we could get but-1-ene out of this. But-2-ene will show EZ isomerism, so we could get a wide range of products out of this. Turning alcohols into alkenes will allow us to produce polymers without crude oil. The alcohol could come from sugar, making this a renewable process. And do not forget to write down that the water is lost, because it is important and I'm guilty of forgetting it a lot. From a reaction is one of your required practicals, and there are lots of different example reactions you could do for this. You could prepare cyclohexene by dehydration of cyclohexanol, distill off the cyclohexene and then test it for a double bond. You could prepare ethanal by the oxidation of ethanol and then distill off the ethanal and use Tollens silver mirror to test for the aldehyde. Hopefully you've managed to do this in the lab and are familiar with quick fit apparatus, which we can see here in the lab where I've done it, and a slightly neater, nicer drawing of what is going on. You need to be aware of the equipment and the safety and where the water goes in and out. That is a very important thing. In the lab, I have used an electronic heater because some of the chemicals involved in this are very volatile. And if we use a Bunsen burner for this, then there is a risk of chemicals catching fire, making it a bit more dangerous. You want to heat this to the boiling point of the required product. Too much and you might get the products you're not looking for. And we're going to be separating things by boiling points. For required practical 6, we are going to be testing for alcohols, aldehydes, alkenes, and carboxylic acids. When you are testing for an alcohol, put ethanol into a dried test tube, add solid sodium, and a positive result are bubbles being given off. We can use a failings test for an aldehyde. A positive solution is the blue turning into a bright orange, so a colour change here. When we are testing for an alkene, we can use orange bromine water. And with a positive result, it will go colourless, not clear, colourless. When we are testing for a carboxylic acid, We can add sodium hydrogen carbonate, and a positive result will be lots of bubbles of carbon dioxide gas being given off. We can confirm that the gas is carbon dioxide by using lime water. If we're going to be testing for halogens, we need to add nitric acid, silver nitrate, and a positive test will be a colour change. For your halogens, the white, cream, yellow are very hard to distinguish from each other, so it's good to have reference samples so you don't get confused. Mass spectrometry can be used to determine the molecular formula of a compound. There are several steps involved. We start with ionization, where electrons are knocked off to give a positive ion. They are then accelerated, so they all have the same kinetic energy, and then they are deflected by a magnetic field. The level of deflection is based on mass and charge. Lighter ions are deflected more, and more charged ions are deflected more. We can use the computer data at the end to determine the formula of the compound. We can determine the identity of organic compounds from a mass spec. For example, here we're going to look at butane. Here is a sample mass spec that we might get from butane. Now, in the ionization stage, it is going to be broken down. The ionization stage breaks it into different parts. The biggest peak will be your molecular ion peak, and the rest of them will be fragments. And from the fragments, we can work out the identity. The peak that has a mass of 29 could be CH3 connected to a CH2. Gradually working out the little bits, starting with the CH3 and then adding on the CH2 and working out the mass. The 43 peak, well, we know it's already bigger than the CH3, CH2 because we've just worked it out to be 29. So if we add on another CH2, just the carbon is 41. Adding on 2 more hydrogens will take us up to 43. Identity of this part and the identity of this part. Now, if we know the compound definitely contains this and has an overall mass of 58, then butane is the logical answer. If it had different molecular peaks, if it didn't contain this, for example, methyl propane will have the same mass and the same formula, but it will give different fragmentation peaks. It will not give this fragmentation peak here. When you have a question showing some data from infrared spectroscopy, you need to look for some characteristic regions. There are 3 you need to know. Different groups absorb infrared at different set frequencies. You will get given a data sheet in exam, so don't worry, you don't need to learn these, but you do need to be familiar with the data sheet and what it looks like. Here are some example graphs. For an alcohol, you are looking for this characteristic region here. If we have a carbon-oxygen double bond, for example, in aldehydes and ketones, you are looking for this characteristic region here. And for carboxylic acids, which will have an OH and a carbon-oxygen double bond, it has kind of a double region, one in the same place as the OH and one in the same place as the carbon-oxygen double bond. You need to be familiar with these characteristic regions on the graphs and be able to refer to them in the exam and pick them out of data given to you in an exam. Infrared radiation is closely linked to the greenhouse effect. The carbon-oxygen double bonds in carbon dioxide absorb infrared radiation, thus preventing it from escaping the atmosphere. The light that we get from the sun is visible light or ultraviolet light. This light is not absorbed by carbon dioxide by the carbon-oxygen double bond. So this light manages to reach the Earth. Once it is emitted from the Earth, it is at the lower frequency radiation, the infrared radiation, that gets absorbed by the carbon-oxygen double bond, preventing it escaping the atmosphere. There are some areas where the language that you use is very important, and thermodynamics is one of those areas. So we're going to go over some key terms. It is important that you learn them well and you can use and apply them properly in an exam. So take your time with this slide, write down the answers, copy down the key terms and learn them. The enthalpy change of formation. This is the standard enthalpy change of formation for a compound, equal to the energy that is transferred when 1 mole of the compound is formed from its elements when they are under standard conditions and in their standard states. Standard conditions is another thing you need to learn. They are 298 Kelvin or 1 atmosphere of pressure. The enthalpy of lattice formation is a standard enthalpy change when 1 mole of ionic lattice is formed from its ions in gaseous form under standard conditions. The enthalpy of lattice dissociation is a standard enthalpy change when 1 mole of an ionic lattice is dissociated into its ions in gaseous form. The first ionization enthalpy is the enthalpy change when 1 mole of electrons is removed from 1 mole of atoms in a gaseous form to give 1 mole of +1 ions in a gaseous form. The second ionization enthalpy is the enthalpy change when 1 mole of electrons is removed from 1 mole of +1 ions to give 1 mole of 2 plus ions in a gaseous form. The enthalpy of atomization is the enthalpy change when 1 mole of atoms in a gaseous form are formed from their elements in a standard state. Bond enthalpy. This is the enthalpy change when 1 mole of a covalent bond is broken homolytically in a gaseous state. Electron affinity is the enthalpy change when 1 mole of atoms in a gaseous form gain 1 mole of electrons to form 1 mole of -1 ions in a gaseous form. The enthalpy change of hydration is the enthalpy change when 1 mole of gaseous ions becomes 1 mole of aqueous ions. It is really important to have accurate descriptions for these terms because these could easily come up as exam questions. Born-Haber cycles, once you get to grips with them, are very, very elegant, but you need to display your working clearly so we don't get confused. We can use them to calculate data that we can't directly measure from bits of data that we can directly measure. Similar to Hess's law, the data will be the same, the answer will be the same irrespective of the route that we take. So here we have sodium chloride as a solid. And we're going to go all the way up to sodium ions and chlorine gas with lots of different steps in between. We have our ions, and that is the electron affinity of chlorine, down to the lattice enthalpy of sodium chloride, the enthalpy change of formation of sodium chloride, the enthalpy change of atomization or the enthalpy change of sublimation, the enthalpy change of atomization for chlorine, and the first ionization enthalpy of sodium. This drawing, this structure, can look very confusing, but if you take it carefully and you take it logically, it's no problem at all. This is where I like to use highlighters in the exam, so you know where you start and you know where you finish and you know which route you are taking. So we can make it very clear which way we're going and which ones need to change sign. So if we want to work out the lattice enthalpy of sodium chloride from start to end in the solid green line, it is a combination of all of the other figures in the highlighted green line. Starting off with the electron affinity of chlorine, we're starting in the same place, but because we are going in the opposite direction to the arrow, it needs to change sign, so it is minus 348. We are then going in the opposite direction of the first ionization enthalpy of sodium, the opposite direction of the enthalpy change of atomization of chlorine, the opposite direction, so it's minus for the enthalpy change of atomization of sodium, and in the same direction as the arrow for the enthalpy change of formation of sodium chloride, so it's a positive, we don't change the sign on that one. Once you have clearly laid out all of your data, and please clearly lay it out so the examiner can see where everything's coming from, and if you make a mistake, we can just do the maths and get the answer at the end. An exam question might start and end in different places. You follow exactly the same method to find different data. A few other things like magnesium chloride. Magnesium will undergo a second ionization enthalpy step and 2 moles of clear minus must be made. All of these numbers are based on real experimental data. Theoretical values can differ based on the covalent character of the bonds. Entropy, or delta S, is a measure of disorder in the system. The higher the entropy value, the more disorder there is, thus the more stable the system is, because there are more ways of rearranging the particles. A reaction can happen spontaneously without any external influence if it's an exothermic reaction, if it has products that are lower in potential energy, and are more thermodynamically stable. But there are some endothermic reactions which are also spontaneous. A solid will have low entropy, whereas a gas will have high entropy. Simple compounds will have low entropy, whereas complex ones will have high entropy. Pure substances will have low entropy, whereas a mixture will have high entropy. We can see that entropy, delta S, is the sum of the entropy of the products minus the entropy of the reactants. If entropy, delta S, is positive, there is an increase in entropy, an increase in disorder, and this will happen when we're moving from a solid to a gas or if we're increasing the number of moles. Delta S is negative, we have a decrease in entropy. If there is an increase in entropy, it is a likely reaction to happen spontaneously. However, if there is a decrease in entropy, it is unlikely to happen. Gibbs free energy has a symbol G, or delta G for changing. If a reaction happens or not is the feasibility of a reaction. This is a balance between delta H and delta S. So delta G, the Gibbs free energy, is equal to delta H, the change in enthalpy, minus T temperature delta S, change in entropy. Delta G is in kilojoules per mole, delta H is in kilojoules per mole, T temperature is in Kelvin, and entropy is in joules per Kelvin per mole. Because we have temperature in the equation, delta G will vary with temperature. If your free energy is negative, the reaction will happen. However, this is nothing to do with rate, so it may happen very, very slowly. If your free energy is positive, then the reaction will not happen. It is not a feasible reaction. If we have a negative enthalpy change and a positive entropy change, it will be spontaneous at all temperatures. However, if we have a positive enthalpy change and a negative entropy change, then it will not happen at any temperature. If both enthalpy and entropy are positive, when delta G is 0, then the temperature will be the enthalpy divided by the entropy, spontaneous above this temperature. We can work out the mechanism for a reaction and the order of a reaction from the data. There is a link between the concentration of a reactant and the rate of that reaction. If we have our equation, we can take this and we can write a rate equation, where rate is K, which is our constant, so concentration of A, X is the order, and B, concentration, and Y is the order. The little numbers in our original equation are the stoichiometric coefficients, that's for the reaction. The superscript numbers in our rate equation are the reaction orders. They are different. We can have a zero order reactant, where the concentration of this reactant has no effect on the rate of reaction. We can have a first order reactant, where the rate of reaction is directly proportional to the concentration. Or it can be second order, where the rate of a reaction is proportional to the concentration squared. The overall order is the individual orders summed. Please recognise the shape of these graphs in an exam. We can determine the units for the rate constant from all the other units. The rate of reaction is using the units moles per decimeter cubed per second. For a reaction that is first order overall, we can look at the rate equation, rearrange it to give K equals rate over the concentration of A, replace what we can with our units, and then start cancelling. And what we have left is seconds to the minus 1. So the units for a first order reaction, first order overall, the units for the rate constant are seconds to the minus 1. For a second order overall reaction, and this doesn't matter whether it is A squared or whether it's the rate constant and then the concentration of A and the concentration of B, because we still have two things there, the overall order of both of those is still second order. Again, we need to rearrange it, so we've got K as the subject, with rate over A and over B, replace what we can with the actual units, and then start cancelling out again. It is worth writing this out in full every time you see it, just to ensure you don't make any mistakes. So if a reaction is second order overall, the units for K are moles to the minus 1, decimeters cubed, seconds to the minus 1. K is for a set temperature, and this will change, this will increase as the temperature increases. When you first see the Arrhenius equation, it can look intimidating, but it is actually very beautiful and elegant once you get used to it. It is important to remember that the rate constant, K, is for a given temperature. The Arrhenius equation describes the link between the rate constant and that temperature. Temperature up the top there is T, this is in kelvins. R is the molar gas constant. You'll get given this value in the exam, you do not need to learn it. However, it is 8.31 joules per mole per Kelvin. EA is the activation energy for the reaction, and that is in joules per mole. That E there, the lowercase e, is the mathematical constant E. The uppercase A is the Arrhenius constant, which is reactant dependent. This is more commonly rearranged in this way, so lnk equals lna minus EA over RT. If it's going to be in graphical format, we're going to have lnk at one side, and then along the bottom we can have 1 over T. The gradient for this is minus the activation energy over R. We can determine the rate equations and the reaction mechanisms. Because, unsurprisingly, reactions are more complicated than the overall equation lets on. Here we have what looks like a very simple reaction. However, that is not what happens. It goes through a series of different steps. In step 1, we've got nitrogen dioxide reacting with nitrogen dioxide to make nitrogen trioxide and nitrogen oxide. Then in step 2, the nitrogen trioxide will react with hydrogen to give us more nitrogen dioxide and water. We can then treat this a little bit like algebra and cross off things that are on both sides of the equation. And what is left over will give us our overall equation for the reaction. The rate equation for this is rate, the constant, and nitrogen dioxide is second order. Changing the concentration of a reactant will affect the rate of the slow step and not the rate of the fast step. Because it is second order with respect to nitrogen dioxide, this is the slow step, the one with nitrogen dioxide in. It is zero order with respect to hydrogen, making this step, step 2, the one with hydrogen in, the fast step. The slowest step will be the one that determines the overall rate of reaction. And this is the rate determining step. We can measure the rate of reaction by initial rate method. This is also known as the iodine clock and is one of your required practicals. The reaction equation for this is hydrogen peroxide plus hydrogen plus iodide ions will give us iodine, the colour, and water. When all of the iodine produced in a reaction has reacted with all of the available thiosulfate ions, which is in reaction 2, any excess iodine is then unreacted in a solution and will turn blue. Altering the concentration of iodide ions, you can experiment and experimentally determine the order of reaction with respect to iodide ions. Here we're going to be measuring the rate of reaction by continuous monitoring. This is between hydrochloric acid and magnesium chloride, and what we're going to get is hydrogen produced here. You can see that I've read through the method and already drawn my table out before the experiment starts. So here I have 0.2 grams of magnesium and 50 centimetres cubed of 1 mole of hydrochloric acid. I'm now going to add them together and use a gas syringe to measure what's collected. So this is quite a complicated experiment to do because your hands need to be doing a lot of things at once. You need to be adding the magnesium to the conical flask at exactly the same time you need to put the bung on, and you need to press the same timer at the same time. We've got a gas syringe here. Gas syringes are quite expensive, quite delicate piece of equipment, so you also need to make sure that this doesn't shoot out the end and smash. So using a bit of skill, I'm going to put that on there, start the timer, and I'm going to keep an eye on the gas syringe. Now every 15 seconds I need to be recording the volume of gas produced. You can see this gas syringe is filling up quite quickly. Sometimes there's a bit of a lag at the beginning as the gas syringe gets stuck, but you can see it's moving quite quickly along. You just need to be careful that your reaction isn't too quick and that gas stream blows out the end. You'll know the reaction's finished when the gas stream stops collecting gas and when the magnesium has disappeared from the hydrochloric acid. So once we finish the reaction, I need to draw my graph here and my line of best fits. Then what you need to do right down here at the beginning is to get your ruler and line your ruler up on the line, and you are going to need to work out the initial rate. So what I've drawn here is a tangent to the line, so we are going to get the line at its steepest part, and then going to work out the gradient of this line here. Draw my tangent, worked out the gradient of tangent, and then worked out the gradient of the line. When you do different concentrations, you can work out the gradient of the line for each of them and compare it. The equilibrium constant, Kp, for reactions involving gas, we are going to be using partial pressure instead of concentration. We need to determine the mole fraction, which is the number of moles of a gas divided by the total number of moles of all gases in the reaction. The partial pressure is the mole fraction multiplied by the total pressure. So for a reaction, we can write an equation. So Kp, the equilibrium constant, will be equal to the partial pressure of C to its coefficient over A over B for this example reaction. At the start, we can assume that there are 100% of the moles of gas are reactant, and we've got 0% no products. For example, in this situation, we're going to have 0.2 moles of gas A and 0.5 moles of gas B. Then we're going to have 1.3 moles of gas C. We can add them all together, so our total number of moles are 2 moles of gas. The mole fraction for gas A is 0.2 divided by 2. We can then find the total pressure. This might be given in the exam, say it's 5 kilopascals. The mole fraction of A, which is 0.1, we can then do 0.1 times 5 to find the partial pressure of A. Kp is going to vary with temperature, but not be affected by a catalyst. We can use cells to work out electrode potentials. A simple cell is a metal electrode in a solution containing that metal. For example, here we have a zinc electrode in a zinc salt solution and a copper electrode in a copper salt solution. A salt bridge is used to connect them together to allow electrons to flow, and this will create the voltaic cell. At each side, we're going to have oxidation or reduction reactions happening. For example, here zinc is being oxidized while copper is being reduced. And we can add those together to give us the overall reaction. From the voltmeter, we can get the E cell for this reaction, and for this example, it is plus 1.10 volts. If we are going to be drawing or writing our cell, our electrode, there is a way that we do that. Zn, solid line, and then the iron, double solid line. Then we need our second iron, solid line again, and then the metal. The double solid line in the middle is representative of the salt bridge. The single solid line will differentiate between the two states, and the most positive one is on the right-hand side. Electrons move from negative to the more positive, and we can predict if a reaction will happen based on the values that we know for each cell. Values are calculated against a reference sample, and this is our standard hydrogen electrode. Here we have our standard hydrogen electrode. We are going to get bubbles of hydrogen coming out of small gaps. We will have a platinum electrode. And because it is the standard reference half cell, it needs to be done under standard conditions. So this is 298 Kelvin, 100 kilopascals, and a 1 mole decimeter cubed solution of the iron. All standard electropotentials are the difference between any given half cell and the standard hydrogen electrode. One of your required practicals is measuring the voltage in an EMF cell. This is a lovely practical and I hope you've had the chance to do it. We need to start off with some very clean electrodes so you can rub them down with a bit of sandpaper and then you can clean them so they're free from grease with some propanone. If your electrodes are not clean, then this could be a source of error in measuring the EMF. The electrodes, the metal electrodes, need to be placed in a solution of the metal ions, and this needs to be connected up to a voltmeter with wires. We can then take the reading from the voltmeter. We need to have a salt bridge. Here the ends are bunged with a little bit of cotton wool and then filled with salt solution in the middle. You can see as the salt bridge goes in and out of the two solutions, a voltage is able to be read on the voltmeter. This is a very old voltmeter, which I have to manually take the reading from myself. You might be able to connect this up to a more sophisticated one, a digital one, to give you a better reading. There are a number of commercial uses for electrochemical cells, including fuel cells. We can have an alkaline hydrogen-oxygen fuel cell. This is made up from a hydrogen half cell and an oxygen half cell. The hydrogen half cell is where oxidation reaction will take place, and the oxygen half cell will have a reduction reaction taking place. The overall reaction for this is half oxygen gas plus hydrogen gas gives us water. Since water is the only product, it is more environmentally friendly than some of the other ways of producing energy. It is highly efficient. However, there are disadvantages to this. Hydrogen is very flammable, making storage difficult and dangerous. The cells will have a limited lifespan. And if we were to do a life cycle assessment of a fuel cell, the production of it involves toxic chemicals, all of which needs to be taken into account. A commercial use for electrochemical cells is rechargeable batteries. Before we get into this, we need to look at a technical definition. The thing that we call a battery, a single AA or AAA battery, is actually a cell. For it to be considered a battery, we need to have multiple cells. So multiple cells are needed for it to actually be a battery. Non-rechargeable cells have an irreversible reaction happening in them. Rechargeable cells involve a reversible reaction. Lithium cells are the ones that are found in mobile phones. If we can charge our phones, they have a rechargeable battery or a rechargeable cell in them. We have lithium and cobalt oxide at the positive electrode. The cobalt will be reduced in this reaction. And we have lithium at the negative electrode. We can write it out in a traditional way that we would recognise from our cells. And see, we still have a salt bridge in there. So the rechargeable batteries that you have in your mobile phones have this smaller version of the very traditional EMF cells that we're used to seeing. Before we look at Bronsted-Lowry acid-base equilibriums, we need to look at a few definitions. An acid is a proton donor. A base is a proton acceptor. And a proton is a hydrogen ion. So hydrochloric acid can dissociate into hydrogen ions, protons and chloride ions. Hydrochloric acid is the acid and the chloride ions are the base. Because HCl, hydrochloric acid, can donate a proton and chloride ions, the base, can accept a proton. NH3 can accept a proton and NH4 plus can donate a proton. So in this situation, NH3 is the base and NH4 is the acid. These will make a conjugate acid-base pair, the part that will accept and the part that will donate the proton. A strong acid is an acid that will fully dissociate. You should be able to recognise some strong acids, for example, hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid. Those are the common ones that you should be familiar with, but just to expand it a little bit, perchloric acid and chloric acid are also strong. So because they fully dissociate, whenever we're doing these calculations, we can assume that the concentration of acid is equal to the concentration of hydrogen ions. For example, if we have 0.1 mole per decimeter cubed of nitric acid, the pH of this is going to be minus log of the concentration of hydrogen ions. We are assuming the concentration of hydrogen ions equals the concentration of acid, so that is minus log 0.1. And here I'm going to put it into the calculator for you so you can see how to actually use it, which buttons you actually need to press, because this is an area people really fall down on. So we can see the pH of nitric acid at 0.1 moles per decimeter cubed is 1. And please do this to 2 decimal places. Nitric acid is a monobasic acid. This is what most of your questions will be about, but I just want to make you aware that sulfuric acid is a dibasic acid. It will have 2 hydrogen ions dissociate, so watch out for this in questions. You might have sulfuric acid giving off 2 hydrogen ions, or it might go to 1 hydrogen ion. Please pay attention to this in the question and check exactly what they're asking you for. If we want to calculate the pH of a strong base, we can use Kw. Water will dissociate into hydrogen ions and hydroxide ions. This will weakly dissociate, so some will dissociate and some won't. If we want to write this as an equilibrium, then we can do it the same as we do the others. Kc with concentration of hydrogen ions on the top, concentration of hydroxide ions on the top, and concentration of water on the bottom. If we rearrange that, we can then take the Kc concentration of water and call that Kw, which is the ionic product of water, and this varies with temperature. At 25 degrees C, Kw is 1 times 10 to the minus 14 mole squared decimeters to minus 6. If we have a strong base, for example sodium hydroxide, that will give us sodium ions and hydroxide ions. Because it is a strong base, we can assume it is fully dissociated, so the concentration, the initial concentration of the base, is going to be equal to the concentration of hydroxide ions. If we want to find the pH of 0.2 moles per decimeter cubed sodium hydroxide at a given temperature, 25 degrees C, we can use Kw. We can write our Kw constant, rearrange it. Replace Kw with 1 times 10 to the minus 14. Replace the concentration of hydroxide ions because we know that from the question, 0.2. Once we have the concentration of hydrogen ions, we can do minus log concentration of hydrogen ions to find the pH. In this case, it would be 13.30 to 2 decimal places. If we want to calculate the pH of a weak acid, it is a tiny little bit more complicated than calculating a pH of a strong acid, but only a tiny little bit more complicated. Weak acids are one that partially dissociate in water. There are a few that you should be familiar with. Methanoic acid, ethanoic acid, benzoic acid, hydrofluoric acid, which is always a surprise to me, and then expanding it a little bit further, nitrous acid, sulfurous acid, and phosphoric acid. When an acid partially dissociates, we can assume an equilibrium is set up, with HA being the hydrogen ion and the base, and A being the base. Here, water is in excess. And because it's in excess, we can rewrite that as HA, so the acid dissociates into the hydrogen ions and the base. We can turn that into an equilibrium equation with a concentration of hydrogen ions and concentration of base on the top and the concentration of HA on the bottom. Ka is the acid dissociation constant. You might also see pKa, which is minus log of Ka, so you'll need your calculator to work that one out. When we are doing these calculations, we can make two assumptions. The first assumption is that the concentration of hydrogen ions is equal to the concentration of base ions at equilibrium. And the second assumption is that HA doesn't change. Because they are so weakly dissociated, we can assume that the concentration of HA at equilibrium is the same as HA at the start. Meaning we can rewrite our equation as the concentration of hydrogen ions squared, because concentration of hydrogen ions equals concentration of base at equilibrium, divided by the concentration of HA at the start, which will generally get given in the question. So we're going to put this into practice. First thing you need to do is to always write down your equation with state symbols and ensure that it is balanced. Work out your equilibrium. And here we're going to be doing concentration of hydrogen ions squared divided by the concentration of ethanoic acid at the start. We know what Ka is because we were told it in the question, so we can replace that. We know what concentration of ethanoic acid is at the start, so we can replace that in the equation. Then we can rearrange the equation, giving us 8.5 times 10 to the minus 7 is concentration of hydrogen ions squared. A little bit of algebra. To get rid of that squared, we need to square root the other side, giving us 9.22 times 10 to the minus 4 as the concentration of hydrogen ions. And always keep your calculator values when you're doing this. If you don't know how to keep your calculator values, use the answer button or the memory buttons and practice with this before you go into the exam, because it is vitally important to avoid rounding errors. pH is the minus log concentration of hydrogen ions, giving us a pH of 3.04 to 2 decimal places. In one of your practicals, you might have done some pH probe work, some titration work, and come up with some pH curves. There are 4 different ones you need to be able to recognise, starting with a strong acid and a strong base. Because they're strong, they're going to start low and end high. A strong acid and a weak base is going to look different. Weak acid and a strong base, and a weak acid and a weak base. The straight up part of the graph in the middle might look a little bit odd. This is the equivalence point. This is where the concentrations are similar or the same, and neither the acid or the base is in excess. Around this point, the pH will change very quickly. When you are doing a titration, you need to pick an indicator. Not all indicators are suitable for all reactions. 2 that you may be familiar with are phenolphthalein, which works at a very high pH, and methyl orange, which works much lower down the pH scale. So when you are picking an indicator, you need to make sure that it is one that will pick up the equivalence point and not be outside of it. A pH probe will work at any value. One of your required practicals is investigating how the pH of a solution changes using a pH probe. We're going to be looking at the reaction between a weak acid and a strong base. The first thing that you need to do is to calibrate your pH probe, because they will never be exactly the same. You need to have your standards so you know what they are, and you need to calibrate them. You will need to wash your probe at every single step to make sure there are no stray hydrogen ions or stray hydroxide ions left over from the last solution. This needs to be done in distilled water to avoid any errors. We can then use our buffer solutions, which we know the value of. We can then see what the value is on the pH probe, and we can draw our calibration curve like this. Here, this should be pH 7, but the probe is coming up as 6.3. We can then do our titration, slowly adding in the different amounts of base, and then recording the pH as the tiny little bits of base get added in. And this is very, very small increments, depending on exactly what your experiment says. You can then draw your graph, your calibration curve, the actual pH versus what the pH should have been according to the buffer, and then adjust your pH readings so that you know what you've actually got. A buffer solution is one that maintains a steady pH, even after additions of small volumes of acid or alkali. An acidic buffer solution is made from a weak acid and the salts of that weak acid. A basic buffer solution is made from a weak base and the salts of that weak base. One example from biology is that blood is a buffer. It will maintain a constant pH of roughly 7.4 and hydrogen carbonate ions are used as the buffer. One example is ethanoic acid and sodium ethanoate as a buffer. When acid is added, the minus ions will pick that up. When alkali is added, hydroxide ions from water will pick up the hydrogen ions, producing more water and shifting the equilibrium to ensure that the equilibrium is maintained. We need to know how to calculate the pH of a buffer solution. As with all long calculations in chemistry, the very first thing that I want you to do is to highlight the key bits of information in different colours if that will help you, and then pull all of the information out. Write it down by the side so you don't need to keep dipping into the complicated question every time you need to get a little bit of information. We've sorted it all out, we've laid it out clearly in one place. So this is all the information we are going to need for this calculation. Because we've got different volumes of our salt and our acid, we can work in moles to make them all into the same volume. So the first thing I'm doing is working out our moles of salt and our moles of acid. We can have our equilibrium equation, and we can rearrange that so we are finding out the concentration of hydrogen ions. We can then replace it with all the numbers that we know. This is the same Ka, so 1.7 times 10 to the minus 5. And because we've put the concentrations into the same volume, we can use moles here instead of concentration. We have our concentration of hydrogen ions. We can then do minus log concentration of hydrogen ions to find the pH. And always use your calculator value. Do not write something down and then use the rounded value that you've written down. You will introduce rounding errors. Use your calculator value and you should get a pH of 4.37 to 2 decimal places. We're going to look at the reactions of period 3 elements with water. Sodium will react to give sodium hydroxide and hydrogen gas. It is a very exothermic reaction that will take place. So you might see flames, you might see fizzing happening. Sodium hydroxide is going to be very, very alkali. Magnesium will react with water to give us magnesium hydroxide and hydrogen gas. This is a much less impressive reaction. It will react slowly with cold water, but quickly with steam. It will still be alkali, but less alkali solution will be produced, roughly pH 10, as magnesium hydroxide is less soluble in water. Sodium will react to give sodium oxide. Magnesium will react to give magnesium oxide. Aluminium metal is generally always covered with a thin layer of aluminium oxide, and to get it to react you need to rub it and it will react again. Silicon reacting with oxygen will give us silicon dioxide. Phosphorus and oxygen will give us P4O10 or P2O3 in limited oxygen. Sulfur reacting will give us sulfur dioxide and some sulfur trioxide, and these are all covalent compounds. The ionic compounds will have high melting and boiling points, whereas the other ones will have lower ones. This is the reaction of period 3 oxides with water. Sodium oxide will react to give us sodium hydroxide. This is a strongly alkaline solution. This reaction is very exothermic. Magnesium oxide will react with water to give us magnesium hydroxide. It is alkaline, but slightly less so at pH 10. Aluminium oxide is insoluble in water, so there is no reaction. Silicon oxide is also insoluble in water. These will give a pH of 7, the pH of water. P4H10 will react with water to give us phosphoric acid. Sulfur dioxide will react to give us sulfurous acid. It will have a pH of 2 to 3, and this is a weak acid. Sulfur trioxide will react to give us sulfuric acid. For the structure of phosphoric acid, for the ion, we lose one of the hydrogens and it is replaced with a negative charge. For sulfurous acid, and again for the ion, one of those will lose the hydrogen and get a negative charge. Similar for sulfuric acid, except we have 2 double bonded oxygens on there, and one of those will lose the hydrogen. Period 3 oxides can also react with acids and bases. Basic oxides will react with acids to produce salts and water. React with hydrochloric acid to give us sodium chloride and water. This follows the very familiar reaction of base plus acid equals salts and water, and works for both sodium oxide and magnesium oxide with whichever acid you would like to react it with. Here, magnesium oxide is reacting with sulfuric acid to produce magnesium sulfate and water. Amphoteric oxides can act as both acids and bases. Aluminium oxide can react with hydrochloric acid, and it is acting as a base to give us aluminium chloride and water. The rest of period 3 form acidic oxides. Silicon oxide will react with very concentrated sodium hydroxide, and only very concentrated as it is insoluble in a weak base or in water. The rest will act as acids as follows. Sulfur dioxide, when released into the environment, is a polluting gas that can cause acid rain. This reaction is one way of removing polluting gases from industrial waste. Transition metals are fascinating things that sit here right in the middle of the periodic table, and the ones you need to know about are titanium through to copper. They will form complexes. They have a range of beautiful coloured ions. They are variable oxidation states, which makes them so useful. And they can act as catalysts. The reason for all of these properties, the reason they are transition metals, is because they have an incomplete D subshell when they're atoms or ions. An interesting thing to point out here is chromium and copper, where the 3D is filled before the 4S. Because it is more stable to have a half full or a full 3D shell than it is to have a full or a half full 4S shell. Zinc is not really a transition metal because it has a full 3D subshell. Neither is scandium. The 4S is a lower energy subshell, so it is removed first. So for cobalt 2+, it will lose everything from the 4S before it loses anything from the 3D. Transition metals can form complex ions. These are made up from a central transition metal ion surrounded by ligands. Ligands will bond in a dative covalent way by donating both of the electrons in the bond. A few new terms we're going to be using, as well as ligand and complex ion: the coordination number, is the number of bonds to the central ion. A monodentate ligand will form one bond, whereas a bidentate ligand will form two bonds. There is a very particular way of drawing these. We will have our transition metal ion in the middle, square brackets, and surrounded by the ligands. When you are writing it out, we have square brackets, the transition metal ion, rounded brackets with a ligand in the middle. The subscript number would indicate the number of ligands, square brackets, and then the charge on the outside. All monodentate 6-coordinate complexes have an octahedral geometry. There are two bidentate ligands you need to know about, ethane 1,2-diamine, and each of them will make two bonds to the central ion, or ethane dianoate. And again, each will make two bonds to the central ion. Both of these have an octahedral geometry. We can also have multidentate ligands. Here we have EDTA, and the 6 places that it forms bonds are highlighted here. Heme in hemoglobin is another multidentate ligand. The hemoglobin will normally bond oxygen, but carbon monoxide will form a stronger bond with the complex. Unfortunately, carbon monoxide is toxic to humans and can result in death. We can have substitution reactions where ligands exchange. There are 3 monodentate ligands you need to be aware of. Water and ammonia are similar in size and are uncharged. The ammonia will replace water, and we'll see a colour change when this happens. We could also have an incomplete substitution, where only 4 of the waters are replaced. Again, we will see a colour change here, but there is not a change in coordination number or in geometry. Chloride ions are larger and they are charged, so we will see some more changes. Not only will we see a colour change, but there has been a change in coordination number from 6 to 4. Also, there will be a change in geometry, as it will now be tetrahedral. This can happen with cobalt, copper, or iron. We can also have ligand exchange by multidentate or bidentate ligands. For bidentate ligands, we have ethane 1,2-diamine and ethane dioate. You need to learn these. However, you do not need to learn the structure of your multidentate ligand, EDTA. The equations for these are very long and look horrific, but they follow exactly the same structure as all of the other ones. There is nothing in here that you can't do. We will be replacing 6 waters with 3 ethane 1,2-diamines. So the exact same coordination number, 6, but because the bidentate ligand makes 2 bonds, we only need 3 bidentate ligands. Or if we're replacing it with a multidentate ligand, EDTA, which has a 6 coordination number, will make 6 bonds, we replace 6 waters with 1 EDTA. And this is the chelate effect. Bidentate and multidentate ligands will replace monodentate ligands. There is an increase in entropy as there are more moles on the right-hand side, with the 6 waters in these circumstances being released. There is little effect on enthalpy due to similar bond energies, meaning this reaction is likely to happen. We need to know the different shapes that complex ions make, because they have a 3D shape. Hopefully you'll be familiar with wedges and dashes from earlier in the course. For a monodentate ligand with a 6 coordination number, we're going to have an octahedral shape. These are for small ligands. For your larger ligands, we're going to have a tetrahedral shape, because the charged chlorides don't really want to be anywhere near each other. We can have square planar complexes, or we can have linear complexes. For example, in toluenes. Complex ions can show cis-trans isomerism. Here we have a platinum central ion, and we can have cisplatin, or we can have transplatin. Cisplatin is a very useful anti-cancer drug. Transplatin is not a very useful anti-cancer drug. For octahedral complexes, where not all of the ligands are the same, they can also show cis-trans isomerism. Or if we have a complex ion that has 2 bidentate ligands and 2 monodentate ligands, these can show cis-trans isomerism. It is well worth spending some time practicing drawing these out in a logical manner. Complex ions can also show optical isomerism. For example, with a hexadentate ligand like EDTA, if we have 2 monodentate ligands and 2 bidentate ligands, or if we have 3 bidentate ligands. These two are optical isomers. As are these two. You'll notice they are mirror images of each other. It is possible for something to show optical isomerism and cis-trans isomerism. Complex ions are beautifully coloured. It's one of the things that makes them my favourite topic. And the change in colour of a solution tells us that something is going on. This could be a change in oxidation state. The ligand or the coordination number has changed. We see colour when some of the wavelengths in visible light are absorbed and removed, and then the rest of the wavelengths are transmitted or reflected. And this is all in the d electrons. We have the average or the ground state of the d electrons. And when they absorb light, they are excited from the ground state. The difference between the ground state and the excited state can be given by delta E equals HV, or Hc over lambda. Delta is our change in, E is energy, which is measured in joules, H is Planck's constant, which is 6.33 times 10 to the minus 34 joules per second. We have the frequency of light, measured in hertz. C is the speed of light, which is 3 times 10 to the 8 meters per second, and lambda is the wavelength measured in meters. If we want to look at the colour or the colour change, we can use spectroscopy or we can use a colorimeter. Transition metals have variable oxidation states. For example, vanadium will lose 2 4s electrons to become vanadium 2+. They will lose the 4s electrons before they lose the 3d electrons, as they are of a lower energy. Vanadium with an oxidation state of 5 is yellow. Vanadium with an oxidation state of 4 is blue. 3 plus vanadium is green, whereas vanadium with an oxidation state of 2 is a lovely violet colour. So we can see lots of colour changes with vanadium, and we can see them all in the following reaction. Starting off with vanadium with a +5 oxidation state at yellow, it will then go through all of the different colours and oxidation states in this reaction to end up with vanadium 2+. We can have silver in a complex ion. And when it meets that functional group, that aldehyde, the silver will come out of the complex ion and you will see a silver mirror. The silver will then form on the outside of the test tube. This is the silver mirror test for aldehyde, and the complex ion with silver in is more commonly known to you as tolerance. The redox potential of any transition metal ion is influenced by the pH and by the ligand. This has a self-indicating colour change, and when we see the colour change, we can answer the question, how much has been oxidised? The important thing to remember when you're working out equations is that the manganate ions are going to be reduced. You're going to have your potassium permanganate in your burette, and then your known volume of the solution that we are analysing goes into your conical flask. This needs to be done in an excess of acid, indicated for this, as the potassium permanganate decolorizes as it reacts. We know we've reached the end point of the titration when we see the first permanent pink colour. This will happen when the potassium permanganate is in excess. Because of the gorgeous deep purple colour of the potassium permanganate, it's really hard to see the bottom of the meniscus. So for these titrations, we read it from the top of the meniscus. If you do this consistency, the difference between the top and the top, then you will still get the actual titers. Again, with this question, we are going to work through sorting out the numbers, and then we are going to do the calculation. So iron sulfate was made up in 250 centimeters cubed solution, and from this 25 centimeters cubed was titrated against 0.02 moles per decimeter cubed potassium manganate 7. The titer needed to oxidize the iron sulfate was 24.2 centimeters cubed. Calculate the original mass of the iron sulfate. First thing we need to do is work out our equations. Now these may be given to you in an exam, or you might have to work these out for yourself. We have our manganate being reduced to manganese 2. And remember, the only thing we can add to these is hydrogen ions, electrons and water. To balance out the 4 oxygens on the left-hand side, we need to add 4 waters on the right-hand side. To balance out the 4 waters on the right-hand side, we need to add 8 hydrogen ions on the left-hand side and 5 electrons to make sure the charges balance. Iron is going to be oxidized, so it's going to start as iron 2 and then get oxidized to iron 3. And for this, we just need to add on our electrons. Now we need to balance these to make an overall reaction, which just means we need to times the bottom one by 5. When you're balancing combining equations, you need to look at the number of electrons. My preference is for you to always write out everything in full so you don't forget things and you don't make mistakes. Then we can go back and cross things off afterwards. We're going to work out the moles of potassium permanganate used. From that, the moles of iron sulfate. From that, the moles of iron sulfate in 250 centimeters cubed. And then we're going to use that to work out the original mass. For our moles of potassium manganate, we can do concentration times will give us 4.8 times 10 to the minus 4 moles. We can look at the ratio in the equation and see that for every 1 mole of manganate ions, we have 5 of iron, giving us 2.4 times 10 to the minus 3 mole. Now we need to work out how much we had in 250 centimeters cubed. To work out the original mass, which is what the question is asking us, mass is moles times mR, which will give us 3.648 grams. Transition metals can act as homogeneous and heterogeneous catalysts. Homogeneous means they're in the same phase, heterogeneous means they're in a different phase, and a catalyst is something that increases the rate of reaction by providing an alternative pathway with a lower activation energy, and that is the key thing here. For a heterogeneous catalyst, generally the catalyst is solid and the reactants will generally be gases or liquids. A catalyst will need to have a large surface area, such as a honeycomb structure, as this is where the reaction actually takes place. The reactants are adsorbed at the active site on the catalyst, and this can weaken the bonds or hold the reactants in a more reactive configuration. When you combine this with a higher concentration of reactants at the catalyst, you will get a higher rate of reaction. Homogeneous catalysts, where the reaction will happen via an intermediate, and the intermediate will generally have a different oxidation state to the reactants or the products. The contact process uses a heterogeneous catalyst, vanadium oxide, in the production of sulfuric acid. step 1, we will sulfur dioxide reacting with vanadium in the +5 oxidation state. And vanadium in the products will be in the +4 oxidation state. The products from the first step, the vanadium 2O4 with vanadium in the +4 oxidation state, will then react with oxygen and go back to being vanadium 5 oxide. We can cancel out some of the vanadium in the 2 different steps to give us the overall equation of sulfur dioxide reacting with oxygen to give us sulfur trioxide. And it is the sulfur trioxide that is actually used in the production of sulfuric acid. The Haber process using a heterogeneous ion catalyst. We have nitrogen mixing with hydrogen to produce ammonia. And this is one instance where a catalyst can be seen to be poisoned by impurities found in the reactants. Poisoning of a catalyst can reduce the efficiency of the catalyst, reducing the yield of the reaction, and increase the cost of the reaction as you will need to replace the catalyst. This is the reaction between iodide ions and persulfate ions. This is a homogeneous catalyst. The overall reaction for this is the reaction between persulfate ions and iodide ions. But this is a reaction between 2 negative ions, and negative ions repel each other. So the activation energy for this reaction is very high and the reaction is slow. The catalyzed reaction is faster. So in step 1, we have our negative persulfate ions reacting with positive iron ions. In step 2, the iron 3+ ions from the products of step 1 react with the iodide ions to remake the 2+ iron ions which were reactant in step 1 and to give us iodide. Iron 3 can also be used to catalyse this reaction. As step 1 and step 2 are not dependent on each other, it doesn't matter which one happens first. Because the catalysed reaction has a positive ion and a negative ion as reactants, it has a lower activation energy, meaning the reaction happens faster. This is the reaction between manganate ions and ethane-dioate. This uses a homogeneous catalyst and is an example of autocatalysis, where one of the products acts as a catalyst, so the reaction will start off slow and then will get faster as more products are produced. The overall reaction has the manganate ions, which are negative, reacting with negative ethane-dioate ions. This is a slow reaction as 2 negative ions will repel each other and there is a high activation energy. In the catalyzed reaction, manganese 2+ will react with the manganate ions and we will have manganese 3+ as a product. The manganese 3+ can then go on to further act as a catalyst, reacting with the ethane-dioate ions to produce manganate 2+. The activation energy of this is lowered. We can then use algebra to cancel out the manganate 2+ and the manganate 3+ ions on either side to come up with the overall reaction. For our metal aqua ions, the acidity of a complex ion which has a central transition metal with a 3+ charge is going to be greater than one with a 2+ charge. As the 3+ ions have a higher charge density, they will attract water more strongly, weakening the bonds, and more easily releasing hydrogen ions. There are lots of metal 2+ reactions that you need to be aware of. You need to know the reactions of copper and hydroxide ions. All of these follow a very similar pattern, so if you learn the example, you should be able to apply it in lots of different situations. You also need to know copper and iron reacting with carbonate ions, and be able to work out the colours of the precipitates. The metal aqua ions with 3+, there are a few reactions you need to know. You need to know iron 3+ and aluminium 3+. Reacting with both hydroxide and ammonia, again, these react in very similar ways, so if you learn the example and practice it applying, you should be able to do it in an exam. And the metal aqua 3+ ions reacting with carbonate ions. These have slightly different products, so you can learn these examples. These will have carbon dioxide and water as additional products. Aluminium hydroxide is amphoteric, which means it can act as an acid or it can act as a base. Again, you should learn these two examples here and then be able to apply them in an exam. We can use practical methods to determine what is in our complex ions. And this is one of the key practicals. We are going to be looking at iron 3 nitrate, copper 2 chloride, and ammonium iron 2 sulfate. If you are using the AQA practical instructions, these are Q, R, and S. Iron 3 nitrate will start off as a yellow solution, copper 2 chloride starts off as a light blue solution, and ammonium iron 2 sulfate starts off as a pale green solution. Test number 1 is going to be the addition of sodium hydroxide. We can do this slowly, drop by drop, until it is in excess. Here you can see my 3 experiments. Iron 2 nitrate will go from a yellow solution to forming an orange-brown precipitate. Copper 2 chloride will go from a light blue solution to have a deeper blue precipitate. And ammonium iron 2 sulfate will go from a pale green solution to a kind of grey-green precipitate. You can see the precipitate because it goes cloudy. In test number 2, we start with 10 drops of sodium carbonate in the test tube and we slowly add in our test solution. So iron 2 nitrate will give us an orange-brown precipitate. Copper 2 chloride will give us a blue-green precipitate. And ammonium iron 2 sulfate will give us a grey-green precipitate. For test number 3, we are adding silver nitrate. Iron 3 nitrate, we will not see any visible change happening here. No change will be observed. For copper 2 chloride, we will see a white precipitate. And unfortunately, I don't have a video for the 3rd experiment here, but what you will see is that there will be a light brown precipitate formed if I had a video of this, which I don't, and I'm truly sorry for that. Optical isomerism is also known as chiral isomerism. Here we have a very simple representation of a compound with a central carbon, and it has bonds to 4 different groups, and this is the key bit here. Because there are 4 different groups, it has a different shape in space. The 2 representations are mirror images of each other. It can be hard to believe it when it's flat, but when you see it in 3D with the Molly it's much easier to understand. These are drawn flat the same way, but you see they are mirror images of each other. They cannot be superimposed on top of each other. These are different enantiomers, and these will affect light differently. Optical isomers enantiomers have similar physical and chemical properties, but will rotate polarized light differently. If the polarized light is rotated clockwise, it is the positive or the D enantiomer. If it is rotated anti-clockwise, then it is the negative or L enantiomer. If you have come across D or L enzymes in biology, this is where it comes from. The majority of reactions will produce a mixture, a 50-50 mixture of each enantiomer. This is a racemic mixture. Because 50% of the light is being rotated clockwise and 50% is being rotated anti-clockwise, there is no overall rotation of light. The difference between the enantiomers is important when we are looking at drugs and enzymes. Some of them will only work with one enantiomer. There are a few famous examples of this. One being thalidomide, where one enantiomer will cause birth defects and the other enantiomer won't. And the other one is ibuprofen, where one is useful and helpful and the other enantiomer isn't. So it is important that drug companies have a way of separating out the enantiomers. We're going to look at aldehydes and ketones together because these carbonyl compounds are very similar. Aldehydes will have a functional group where the carbon is double bonded to an oxygen and a hydrogen at the end of a group, whereas a ketone, the functional group will be in the middle, a carbon double bonded to an oxygen. This aldehyde you can see here in the molemods is butan-al. The al bit tells us it's an aldehyde, and so on at the bottom is butan-one. One bit tells us it's a ketone. They are soluble in water due to the ability to form hydrogen bonds. There are two tests to tell the difference between aldehydes and ketones. We have a test with Tollens reagent and we have a test with Fehling's reagent. I have covered both of these in more detail earlier in this video. Both will only give a positive result with an aldehyde. So Tollens will give us that very distinctive silver mirror on the inside of the test tube, whereas Fehling's will go from blue to red or brick red, a brick red precipitate. A primary alcohol can be oxidized to an aldehyde, and this aldehyde can be further oxidized to a carboxylic acid. A secondary alcohol can be oxidized to a ketone. And just as a quick reminder that tertiary alcohols cannot be oxidized. You will see the distinctive orange colour being reduced to a dirty green colour of your chromate. As we can have oxidation, we can also have reduction, which is going in the opposite direction. This is a nucleophilic addition reaction, and it will need sodium tetrahydroborate in aqueous solution. This will give us hydrogen minus ions. We can have ethanal with its partial charges within the molecule being attacked by the hydrogen nucleophile. This will give us an intermediate ion, which will then interact with hydrogen plus ions to give us a primary alcohol at the end. For our ketone, it is a similar reaction. We have partial charges within the molecule, and they are attacked by the nucleophile hydrogen minus. Again, we will get an intermediate, which will react with H plus ions. This will give us a secondary alcohol. They can also be reduced using potassium cyanide. This needs to be done in acidic conditions and it will give us the cyanide, the Cn minus ion. The acidic conditions will give us the hydrogen ions. Hydrogen cyanide is a highly poisonous gas. Potassium cyanide is also highly poisonous, but it is a solid, making it slightly safer to handle in a laboratory and is used in preference. We have our aldehyde with our partial charges within it. that is going to be attacked by the negative charge on the cyanide, and it's going to give us an intermediate. That is going to react with the H plus ion to give us our end product. Now, lots of students forget that cyanide is actually carbon and nitrogen, so our longest carbon chain in here actually goes into the cyanide, the CN. That is a carbon in there. So we now have a 3-carbon chain here, making this 2-hydroxypropanenitrile. Here we've gone from an aldehyde to a hydroxynitrile. We have a similar reaction with our ketone. We have our ketone here, propanone, and it has partial charges in there. The delta positive carbon in there will be attacked by the nucleophile. We will get our intermediate, and then we will get our final product at the end. Now, naming this one is going to be a little tricky because we need to look at our higher priority functional groups. So we have 2-hydroxy, 2-methyl propanenitrile. The methyl is a group, the hydroxy is a group, but the nitrile is the higher priority group, so it is the main stem of the name. The hydroxynitrile that we got from the reduction of an aldehyde has a chiral carbon there in the middle. So the reduction of aldehydes and asymmetric ketones will produce enantiomers. When we are drawing and naming carboxylic acids, it is this group here at the end that we are looking at. That's the functional group that tells us it's a carboxylic acid. This is propanoic acid. The oic acid bit at the end tells us from the name that it's a carboxylic acid. These are weak acids. The hydrogen ion will dissociate and there will be a delocalized negative charge over the 2 oxygens. We can get salts of carboxylic acids. Here, if the sodium positive ion is attracted to the negative charge, we can get a sodium propanoate salt. We can identify carboxylic acids as they will react with carbonates to give off carbon dioxide gas. You can confirm the identity of carbon dioxide gas using the lime water test. Esters are made when we react carboxylic acid with an alcohol. Here we have ethanoic acid and propan-1-ol. And then we have our ester coming out of it at the end. The name of the ester comes from the alcohol and the carboxylic acid. So ethanoic acid and propan-1-ol will give us propyl ethanoate. We will also get water out at the end of it, and the highlighted atoms in here are the ones that go on to make water. For the condensation reaction, it's going to need to be reflux and concentrated sulfuric acid. For the hydrolysis reaction to take place, there are 2 different ways this can happen. With acid, it is reflux with dilute hydrochloric acid, or in alkaline conditions, it is reflux with sodium hydroxide. In alkaline conditions, we will then numb up with a sodium salt of carboxylic acid. Esters can be used in a wide range of things. They can be used as plasticizers in polymers. They are very sweet smelling, so they can be used as flavors or perfumes. And they can be used as solvents for polar organic solutions or substances. Animal fats and vegetable oils are made up from propan-1,2,3-triol, which is also known as glycerol, and long-chain carboxylic acids, which are also known as fatty acids. Each fatty acid will react with an alcohol group in a condensation reaction to give us our very large ester and water. Oils and fats can undergo hydrolysis reactions in alkali conditions, and this will give us glycerol and salts of our carboxylic acid, and these can be used as soap. Biodiesel is made up from methyl esters of carboxylic acids. Here we have our ester We can react it with methanol to get glycerol, which is, remember, propan 1,2,3 triol, and our methyl esters. Acid anhydrides have a rather complicated looking functional group, but it's really not that scary. This is ethanoic anhydride, and this is safer to use, or acid anhydrides are safer to use than acyl chlorides in the manufacture of aspirin or other industrial processes. Acyl chlorides will give off hydrochloric acid as a toxic byproduct, whereas acid anhydrides will give off carboxylic acids. Acid anhydrides will react with water. And I've drawn the acid anhydride, the two different halves, in different colours here, because when the acid anhydride reacts with water, it will give off carboxylic acids. They don't have to be the same carboxylic acids. Here is giving off two different carboxylic acids. For this reaction, you just need water and it will occur at room temperature. Acid anhydrides will react with alcohol to give us an ester and a carboxylic acid. For this reaction, you need alcohol and it will occur at room temperature. Acid anhydrides will react with ammonia to give us a primary amide and a carboxylic acid. If there is excess ammonia, this carboxylic acid can be turned into a salt. For this, you need ammonia and the reaction will occur at room temperature. Carboxylic acids will react with primary amines to give us secondary amides and a carboxylic acid. Again, if we have excess, then we can get a salt from the carboxylic acid. For this reaction to occur, we need the primary amine and it will occur at room temperature. Acyl chlorides have a similar structure to carboxylic acids or aldehydes with the carbon double bonded to an oxygen, but the other thing bonded to the carbon is a chloride. This is much more reactive than carboxylic acids. Because it has this internal dipole, it can be attacked by a nucleophile. In a slight mouthful of a nucleophilic addition elimination reactions. For the following reactions, you not only need to know the products, but you need to know the reaction mechanisms as well. How to draw the reaction mechanisms, where the arrows start, where the arrows go to. Acyl chlorides can react with water. With water acting as our nucleophile, it will attack the carbon atom there in the middle, where we have a partial dipole set up. It will give us an intermediate ion. And then at the end, we will get carboxylic acid and hydrochloric acid. For this, you need water and it will occur at room temperature. Acyl chlorides will react with alcohols. This is a very, very similar reaction. You can see I've just replaced one of the hydrogens with a CH3 group. If you learn one of these mechanisms, you should be in a really good place to do all of the mechanisms. The oxygen, the nucleophile, will attack the carbon there with a partial positive charge. We will get an intermediate setup. And our products at the end will be an ester and hydrochloric acid. For this, you need alcohol and the reaction will occur at room temperature. Acyl chlorides will also react with ammonia. In a very similar reaction, the nitrogen, the lone pairs on the nitrogen this time, will target the carbon with a partial positive charge, giving us an intermediate. At the end, we will get a primary amide and hydrochloric acid. For this reaction, you need ammonia and it will occur at room temperature. Acyl chlorides will react with primary amines to give us secondary amides and hydrochloric acid. This reaction needs a primary amine and will occur at room temperature. We're going to be testing the purity of this solid. Here I have a melting point tube, which is a very, very fine tube, which has an opening on each end. And what I need to do is just fill this with the organic solid to about 5 millimeters in depth. Now, you don't want to get stuff on the end, you just want it in the
centre of the tube here. So this is our rather ancient melting point apparatus. These are our melting point tubes with a tiny bit of our solid that we just made in there. And then what we need to do in the top here is place in the thermometer 3 samples and test the melting points. And we can see through this little hole here, we can see our 3 samples, and what we need to be watching is for when they melt, and they should all melt at a certain point. It shouldn't be over a range, and that will tell us that it is a pure sample. So you can see here that the sample has melted and it is way below the temperature that it should be, because it went at about 78 degrees and we wanted it to be between 100 and 120. So a bit of a fail for us there, but you can see how the melting point apparatus works. So here we're going to be using a round bottom flask, and obviously these are round, so to hold that steady I'm just going to put it in a large beaker to hold it as a secure base. We are going to make an organic solvent, so I have 50 centimetres cubed of ethanol, .50 centimetres cubed of glacial ethanoic acid. This stuff is quite nasty. We are going to use some quite nasty things. I'm doing all of this in a fume hood. And give that a bit of a swirl to mix it. And then really slowly I'm going to add some concentrated sulfuric acid. You can see, if you look closely, the concentrated sulfuric acid changing the look of it because it's concentrated. Then I finish in the fume hood. So after mixing all those things, I've set it up to reflux. Here I have my mantle. You could use a Bunsen burner or a water bath if you don't have one of these available. Here's my round bottom flask. This is just sitting ever so slightly above the basket here, so it's not sitting on it, it's sitting also slightly above it. I've got my connector and I've got my reflux condenser here. The important thing to remember with reflux is that the water needs to go in at the bottom, the cold water comes in here, and then the hot water, or the water that's been warmed up a little bit, needs to go out at the top. So you can see this is bubbling away now, and if we look really, really carefully in here, you can see, if I just wiggle you around a little bit, you can see that it's evaporating and it's condensing. So you can see that the cold water is causing anything that's evaporated to condense and then drop back down into the flask where it can be reboiled. So reflux just lets the same things be reboiled over and over again. After it's been refluxing for about 10 minutes, we just need to change all the equipment also around, so it's now going to distill. Now we've set this up for distillation. We've got exactly the same bottom flask bubbling away here. We've got a corner stopper on here, and we've got our condenser, and then everything that's distilling off is collecting in this little beaker here. If I show you the drops. So it evaporates, it condenses, and then the gas is sent along here, and it condenses, travels all the way down here and drops into the end. So now we've distilled off 2/3 of our solution, we need to add some sodium carbonate to it and put it in a separating funnel. So you need to make sure that it's closed when it is in line, it's open. When it's not in line, it's closed. So I'm going to take the stopper off the top, pour in my sodium carbonate, pour in my solution that we've just distilled here, and then what you need to do is pop the lid back on this. We're going to be inverting it, so we need to make sure that it's quite secure. You're going to need to have quite a firm hold on this. Invert it several times to give it a mix, and what you need to do is open the tap to release any gas that comes off. I would do this maybe 2-3 times. Invert it until you stop hearing that it'll fizz, that it will release. That tells you a gas has been produced. and then turn it back up the right way and allow it to separate out into two different layers. You can already see here that we've got a lower layer and top layer separating out. I'm just going to leave that for a bit, and then I'm going to take it over here and pull off the lower layer. Now you can put this in a clamp if you want to. I'm just going to hold it for a second. So I've just opened this tap ever so slightly. If I want to open it fully, it will go faster, but I want to have control over how this works. So I'm just opening it drop by drop, and we are going to be discarding the lower layer in this case, and we're going to be keeping the top layer. So it doesn't matter if a little bit of my top layer goes out and gets discarded with my lower layer, that's absolutely fine. If we wanted to be keeping the lower layer and discarding the top layer, then I would stop so there's a little bit of the lower layer still in here, but since we're going to be discarding the lower layer, I'll stop that, let it settle down for a bit. Since we're going to be discarding the lower layer, I'm going to go ever so slightly past the line, so I lose a little bit of my top layer, but I make sure that it's all pure. So I'm just going to slow that down so I don't like bubbles. You can see the layer is just here. Stop that. Drop a couple more views so I can still see the layer. It's just about here now. Now in here I just have my top layer, and that's what I'm going to use for the next parts. So now that I've done that once, I need to do that again with 20 centimetres cubed of saturated calcium chloride. So my stopper is closed, and this is the top layer from before. So in that goes. Again, I need to mix it. Put that in there, make sure it's secure grip. Mix it a couple of times. Open the tap to release the gas. Mix it a couple more times. Open the tap to release any gas. And then keep mixing it until you can't get here any more gas released, and let it separate out. So again, we can see two layers separating out here, and again I want to discard the lower layer. So I'm just going to run this off until the layer has gone all the way through. Just going to release a bit of pressure at the top and start running that down there. Okay, so it goes quite quickly once you take the top off. I'm just going to let it settle out for a little bit, and then go very slowly, drop by drop, watching the part between the layers separate out through. And then here I just have my top layer left. So now that I've just got my top layer, I'm just going to let that go through into there, taking the top off to release any gas. Now I'm just going to add some solid anhydrous calcium chloride. Doesn't say how much, so I'm going to add that much. Give it a bit of a swirl. And then what I need to do is to transfer the liquid into a round bottom flask and set up a distillation again. Now we're going to distill off again, but what we've added into the apparatus is a thermometer just here. So what we can do is collect of the different fractions which come off at different temperatures, because we only want a certain fraction. We are waiting for something to distill off between 74 and 79 degrees, so everything that is coming out at the moment we can just discard.
There is an old joke in organic chemistry that you spend 10% of your time learning chemistry and 90% of the time learning how to draw perfect hexagons. To help me draw perfect hexagons, I've got this paper, which you can download completely free off my website. Benzene is a hexagon with a circle in the middle. It is made up of 6 carbons and 6 hydrogens. It is an aromatic 6-carbon ring with 6 delocalized electrons in the middle. That's what the circle is showing us. When the structure of this was being determined, it was hypothesized this is actually cyclohexa 135 triene with double bonds in there, alternating between double and single bonds. However, there is some evidence that supports the ring structure with delocalized electrons over the double single bonds alternation. It has a planar structure. It is flat. If it was alternating double and single bonds, you'd expect there to be a change in geometry. The bond length in benzene is an intermediate bond length between single bonds and double bonds. Benzene is more stable than cyclohexa 1,3 triene should be. If we look at the enthalpy of hydrogenation, the actual experimental value that we get is different to the theoretical value, showing it is more stable. These are the important bits you need to know for the exam, but I don't think it hurts to tell you that benzene also doesn't react with bromine water, again suggesting there are no double bonds. There is a very specific mechanism you need to learn for the nitration of benzene. Step 1, we are generating the electrophile. For this, we need sulfuric acid and nitric acid. This will give us H2NO3 plus ion and a HSO4 minus ion, which I'm just going to rub out because we don't need that for the moment. The H2NO3 plus ion will then go on to give us water and NO2 plus. For step 2, we have our benzene and it is going to react with our electrophile, the NO2 plus. We are going to get an intermediate. Our HSO4 minus ion will come and take that hydrogen ion and the catalyst will be regenerated. We will then get nitrobenzene. For this, we need concentrated nitric acid and our catalyst is concentrated sulfuric acid. And it needs to be refluxed at a moderately high temperature. You need to be able to draw some acylation reactions. The first step is the formation of the electrophile. We have aluminium chloride and our acyl chloride, which is going to give us the electrophile. Step 2 is the actual electrophilic substitution reaction. The negative benzene ring is going to be attracted to that positive charge on that carbon. We're going to get an intermediate. The negative AlCl4 is going to drag off that hydrogen, giving us our product, reforming the catalyst and hydrochloric acid as a byproduct. We can start this by looking at the naming of aliphatic amines. This has 3 carbons in it, so it's going to be propyl amine. Similar to alcohols, we have primary, secondary, and tertiary amines. Propyl amine is a primary amine. But if your amine is in the middle, if it has 1 hydrogen attached to it, not 2, it is a secondary amine. So this one would be N-methyl, which is that group there. Ethyl, which is the other alkyl group. 1-amine. And the N tells us it's a secondary. If it has 2 N's, it will be a tertiary. And you could look at the name to build up the groups around it: methyl, ethyl, propyl, etc. If we have ammonia and a halogenoalkane, we'll get a primary amine. Here we have our primary amine, and the ammonia, the lone pairs on the nitrogen on ammonia, are going to go in and get that carbon. We're going to have a positive intermediate where more ammonia is involved, and this will give us our primary amine as a product. This is a nucleophilic substitution reactions. We can also go from a nitrile to a primary amine. Step 1 would be the halogenoalkane plus cyanide ion, come from something like potassium cyanide, to give us our nitrile set up here. And then in step 2, we can take our nitrile, reduce it to give us our primary amine. In this situation, the hydrogen for reduction comes from LiAlH4. When we have aromatic amines, we're going to take our nitrobenzene and add in a reducing agent. That's hydrogen in square brackets, which is going to turn the NO2 group into an NH2 group and water. This will give us phenylamine. We can use tin or iron as a catalyst, and we need to heat it with hydrochloric acid. Phenylamine is used in the manufacture of dyes. Amines can act as bases as they can accept a proton. Starting with the weakest, we have aromatic amines. Here we have phenylamine. For this to be able to accept a proton, it needs to be added on to the nitrogen. However, the lone pair of electrons on the nitrogen has joined the delocalized electrons in the middle of the ring, so it is not available to accept the proton. Ammonia comes in the middle, so we have NH3 plus H2O gives us ammonium and hydroxide. And then of the three of them, primary amines are the strongest bases. This is because the electrons move towards the nitrogen, increasing the electron density. So it can more readily accept the hydrogen ion, it can more readily accept the proton, making it a better base. There are lots of reactions of amines. These can act as nucleophiles. A halogenoalkane plus ammonia will give us a primary amine. This primary amine plus a halogenoalkane will give us a secondary amine. This secondary amine plus halogenoalkane will give us a tertiary amine. This tertiary amine, you can see where I'm going with this, can't you? Plus a halogenoalkane will give us a quaternary ammonium salt. You do need to know the mechanisms for these, however, every single step is very, very similar. So if you learn the first one properly and carefully, you should be fine. Here we have halogenoalkane and ammonia. The ammonia, the lone pair, is going to be attracted to the carbon, and then the bromine is going to get shifted out of the way. We're going to have an intermediate, which ammonia is going to be attracted to again, and then we are going to have our primary amine. We're going to start from the same place, the same halogenoalkane, except this time instead of ammonia, we've got our primary amine. It's still exactly the same with the lone pair on the nitrogen being involved. Our intermediate this time is slightly more complicated, but only slightly more complicated. Ammonia is still going to do the same thing in the same place. And our product at the end is going to be a secondary amine. These may look really horrible and complicated, but once you get used to drawing it, it's fine. Starting with the same halogenoalkane again, we are then going to be using our secondary amine with nitrogen acting exactly the same way. Our intermediate is looking a little bit more complicated, but ammonia is going to be doing exactly the same thing. And we're going to end up with a tertiary amine at the end. Back again to our halogenoalkane, and this time we have our tertiary amine, the nitrogen that being involved. And this time we go to a quaternary ammonium salt. And these are used as cationic surfactants. Condensation polymerization occurs between dicarboxylic acids and diols, dicarboxylic acids and diamines, or between amino acids. Dicarboxylic acids and diols will give us polyesters because that's the linkage. Dicarboxylic acids and diamines will give us polyamides because that is the linkage. And amino acids will polymerize to give us proteins. Here we have our dicarboxylic acid with the carboxylic acid group on either end, and our diol with an alcohol group on either end. There will be a condensation reaction between the two, and there will be an ester linkage set up. Please note carefully how I'm drawing this with a bond extending outside of the square brackets, large square brackets surrounding everything, and the ester linkage in the middle. A condensation reaction is one where we lose a small molecule. Most of the time this is water, as we have lost here, but you can also lose hydrochloric acid. Our diester is benzene 1,4-dicarboxylic acid, reacting with ethane 1,2-diol. And this will give us terylene, which is a fabric. Here is another dicarboxylic acid reacting with the diamine. We're again going to have a condensation reaction and lose water. Our dicarboxylic acid has 6 carbons in, 4 here in the middle, 5, 6, giving us hexane dioic acid. This is reacting with hexane 1,6-diamine to give us nylon 6,6. You can have different numbers in the middle of nylon. You can have nylon 4,6, depending on the number of carbons in the middle. Both polyesters and polyamides, nylon, terylene, are used as fabrics. Here is another example of a dicarboxylic acid reacting with the diamine. We will lose water again. This time we have benzene 1,4-dicarboxylic acid reacting with benzene 1,4-diamine, and the common name for the product is Kevlar. This is used in bulletproof vests. Here we have a polymer of Kevlar, and you can see within lots of the bonds here there are partial dipoles. So that when we get 2 polymers lining up next to each other, we can get bonding between the polymers happening. We can get hydrogen bonding occurring between the oxygens in the carbon-oxygen double bond and the hydrogens in the nitrogen-hydrogen bond, giving very strong bonds between strands of polymers. Biodegradable polymers are a brilliant alternative to sending polymers to landfill. Polyesters and polyamides are made by condensation reactions, thus they can be broken down by hydrolysis reactions. This makes them biodegradable. Polyalkenes from addition polymerization are not biodegradable. They cannot be broken down by hydrolysis reactions. These must be disposed of in one of the following ways. With recycling, the advantage is that it reduces the need for the finite raw materials. Lots of polyalkenes are made from crude oil, and this is finite and has lots of other uses. When they're recycled, they can be melted down and made into other things and reshaped. However, the disadvantages is that they need to be collected and sorted out, since each type has to be melted down, has to be recycled with its own type of plastic. You cannot mix different types of plastic when you are recycling, trying to make something new. Things can be sent to landfill, and I will admit I did struggle to find an advantage for sending things to landfill, but it is a very commonplace thing to do, and we have the systems in place for it already. It's pretty easy. However, we are running out of space to put stuff. Our landfills are filling up rapidly. Things that are already in there take years and years to break down. There is also the issue of pollution, visual pollution, air pollution from the degradation of things and mixing of products. Polymers can be used as a fuel, which can be used to generate electricity and energy. The disadvantage of this is the toxic air pollution that comes from this. Amino acids might feel like a biology topic, but there is lots of chemistry involved here. You can see with the mods, I'm going to make all of the different amino acids, and you can see in the background here we have the general structure, with this pink bit being the general R group. You need to know the general structure of amino acid. We have a carbon in the middle, and this R is the R group. That can be replaceable with any different things to make the different amino acids, but it will always have the same basic structure: an amino group on one end and a carboxylic acid group on the other end. The R groups are changeable, and that will lead to all of the different properties. This carbon in the middle means it is chiral in nearly all circumstances, apart from when the R group is H, and then it is not chiral. You do not need to remember all of these common names that are being displayed up here. Not even the biologists have to do that. But it is expected that you'll be able to apply your skills in chemistry to naming a few of them. I've gone over all of them, all the ones you'll be expected to sensibly name in a whole separate video. An amino acid is a Zwitter ion, meaning it can have a positive charge on one half and a negative charge on the other half. In low pH, we are going to lose the negative charge, and in high pH, we're going to lose the positive charge. This property of amino acids is an example of them acting as a weak buffer. There are different levels of structure within proteins. Here we have two amino acids. They're going to have different R groups, so I've drawn them as R and R'. We're going to have a condensation reaction between the amino group and the carboxylic acid group. This is going to give us a peptide linkage in the middle. Our monomer here is an amino acid, and two of them joined together is a dipeptide. This is a condensation reaction, so we will lose water. You can take your dipeptide or your protein chain, and it will undergo a hydrolysis reaction to remake the constituent amino acids. The long chain of different amino acids is the primary structure. This will fold up in two different ways to make the secondary structure. They will either be an alpha helix or a beta pleated sheet. The next level of folding will give us the tertiary structure, within which you can see helices and pleated sheets. There is then the complex quaternary structure, which is more than one polypeptide chain. The structure of the alpha helix and the beta pleated sheet is held together by intermolecular bonding. These can be hydrogen bonds, as you can see here, disulfide bridges when your R group has a sulfur in it, or ionic bonds. All of these help to hold together the secondary and the tertiary and the quaternary structure. Enzymes are very complicated proteins. They generally have a quaternary structure. The active site of an enzyme, where the reaction actually happens, is very specific for the substrate. So it might only work with one enantiomer. Most amino acids are either L or negative enantiomer. This orange representation here, this enzyme, is required for the maturation of the coronavirus. If we know the shape of the active site of the protein, then chemists can develop inhibitors which will fit in the middle here, drugs that can block the active site and can be effective medicines. There is a lot of computer-aided design that can be used in the development of drugs. If we know what the structures look like and we know what the active site looks like, we can play around trying to fit things in. You need to know the structure of DNA, and you might be aware now that I love molymods. So here is my molymod building of DNA. The structures are given to you on the data sheet, so you do not need to learn these, but you do need to be familiar with them. You get given the phosphate ion and the 2-deoxyribose, and you get given the structure of all of the bases. There are 4 DNA bases that you need to know about, and another one that's just in RNA, but that's a bit more biology. The purines are guanine and adenine, and the pyrimidines are cytosine, thymine, and only in RNA, which is a bit beyond this, uracil. C and G will make 3 hydrogen bonds to each other, and A and T will make 2 hydrogen bonds to each other. A nucleotide is a phosphate ion plus a 2-deoxyribose plus a base. A strand of DNA is a polymer of nucleotides. And your overall structure of DNA is a double helix of 2 complementary strands. Cisplatin is a complex ion. It has platinum in the middle. It has 2 chloride ligands and 2 ammonia ligands. And it is cisplatin that we are interested in as an active anti-cancer drug. Transplatin is not active as an anti-cancer drug because of the different structure. Here you can see cisplatin in the DNA. The chloride ions in the structure are replaced by nitrogen in guanine. This is a ligand substitution reaction. The helix shape is deformed and DNA replication is prevented. So it is effective at stopping cells replicating, an effective anti-cancer drug. But when you're using it, there needs to be a balance between killing off the cancerous cells and killing off the healthy living cells, because there will be negative side effects from killing off healthy living cells. The next 2 slides are going to be summary slides of all of the organic reactions that we've come across in the course so far. It is going to go pretty quickly because I've gone over these in detail in other places in this video. What you can do is pause this slide and copy down the sections that you need and practice going from place to place. If you want a more detailed video where I go through lots and lots of examples of going from one place to another place, that video is already made for you. It's already waiting for you. But this is going to go pretty quickly. We're going to put some nice music over it. I don't expect you to keep up. I expect you to pause it, copy stuff down, and then use that to answer questions. Proton NMR is very similar to carbon NMR, but the big difference is the amount of information we get given in the spectra and how we read it. The number of different sets of peaks that we have shows the number of different environments we're looking at. The chemical shift will show us the type of environment that we're looking at. The integration numbers will show us the relative number or the ratio of hydrogens that are in that environment. And then the spin coupling pattern will show us the adjacent hydrogens. When we're looking at chemical shift, TMS is going to be the standard. This is given the value of 0 and everything else is compared to this. This is tetramethylsilane and it is used because it is symmetrical. So all the protons are in the same environment. The solvent we're looking at could be deuterated chloroform. And deuterium doesn't absorb, so it won't give a peak. Other ones could be deuterated dimethyl sulfoxate. When we're looking at spectra, we are going to have a line across the bottom that's going to show us how far shifted along things are. And this is going to tell us the type of environment that the protons we're looking at are in. For example, if it's between 7 and 8, then chances are it's part of a benzene ring. And if it's all the way over by 11, then chances are it's part of a carboxylic acid. This is all going to be shown on your data sheet. So here we have a very simple hydrocarbon. And if we look at this hydrogen, if we look at this proton, it is in an environment. We can say that proton is attached to a carbon that has 3 hydrogens attached to it. Whereas if we look at this second one, it's got a slightly different proton environment set up. There are 3 different types of environments. The pink protons are all the same. We can describe each of these pink protons as being attached to a carbon that is adjacent to a carbon that has no hydrogens on it. And there are 3 protons that we can describe in this way. So there are 3 protons that are in an identical environment. The purple protons can be described as being attached to a carbon which is attached to a CH3 group, adjacent to a CH3 group. And there are 2 protons in this environment. The orange ones can be described as being attached to a carbon that is adjacent to a CH2 group. And there are 3 protons in this environment. So for these pink protons, if on a spectra it is adjacent to no hydrogens, then it becomes as a single peak. And because there are 3 protons in this environment, it is going to have an integration number of 3, or be 3 high. The purple ones are adjacent to a CH3 group, which means it will show up as 4 peaks. And because there are 2 protons in this environment, the integration number will be 2. The orange ones are adjacent to a CH2 group. And there are 3 protons in this environment. And then where they are on the spectra is all to do with the chemical shift, the type of environment that they are in. If we want to work out what the split pattern is saying, we need to think about the n+1 rule. The number of peaks in the splitting pattern will be 1 more than the number of hydrogens attached to the adjacent carbon. For example, if there are no hydrogens attached to the adjacent carbon, 0 plus 1 gives us 1, which means we'll have a single peak, which is called a singlet. If it's adjacent to a CH, 1 plus 1 is 2, means we will get 2 peaks, or it will look like a doublet. If it's adjacent to a CH2, 2 plus 1 is 3, we will get 3 peaks, or a triplet. If it's adjacent to a CH3, 3 plus 1 is 4, means we'll get a quartet with 4 peaks. When you do a lot of these, you will start to recognise some patterns and some pairs of patterns that come up frequently. Now, these pairs of patterns may not be directly next to each other. We can have 2 doublets, which means there's going to be a CH group and a CH group. We can have 2 triplets, which means there's going to be a CH2 group and a CH2 group. We can have a triplet and a doublet, meaning we're going to have a CH group and a CH2 group. We could have a quartet and a triplet, showing a CH2 group and a CH3 group. A quartet and a doublet with a CH group and a CH3 group. Or a multiplet, which this one has 7 peaks in it. Now, thinking about our n+1 rule, 7 peaks is going to mean 6 hydrogens, And the most common example of this is going to be two CH3 groups or two methyl groups attached to the same carbon. Now, when we are looking at peaks, you have to remember that it is next to. So the CH2 group is responsible for the triplet, and the CH3 group is responsible for the quartet. Carbon NMR can tell us quite a lot of information about a compound. The number of peaks tells us the number of different environments, and the chemical shift tells us the type of chemical environments. Chemical shifts are going to be given on the datasheet, but you should be familiar with reading them. Things over on the far left are generally going to be a carbon, double bond oxygen. The chemical environment of a particular carbon atom is determined by its location within a compound. It depends on what it is bonded to and what it is next to. Here we can look at a couple of examples. All have the same formula but a different arrangement in space. We can look at the different carbon environments. Butanol has 4 different carbon environments. Whereas as we move through the compounds, we can start to see that the methyl groups become interchangeable and they are in the same carbon environments. If something has 4 carbon environments, it will have 4 peaks on a carbon NMR. If something has 2 carbon environments, it'll have 2 peaks, and 3 carbon environments, 3 peaks. Chromatography can be used to separate out different things in a mixture. Thin layer chromatography has plates that are coated in solid. You will need to very carefully, with a capillary tube, dot on your sample. The plates are coated with stationary phase. This is the solid, whereas the mobile phase, the bit that will actually be moving up, is the liquid, the solvent. Once your plates are dry at the end, you can work out the RF value by doing the distance moved by the spots divided the distance moved by the solvent. And it is really important that you are consistent when you're doing this and you pick the centre of the spots. They are never going to be beautifully neat. This can be used to separate amino acids, and you can visualise the spots using ninhydrin or UV. This is based on the separation being a balance between solubility in the mobile phase and retention in the stationary phase. Column chromatography is a bit more complicated. We have a column filled with powder or beads to give it our large surface area. This is the stationary phase. The mixture that you want to separate out will be dissolved in solvent, and the mixture will separate out in the column. The time for each part to leave the column can be recorded and each fragment can be identified. Even more sophisticated is gas chromatography, which works on very similar principles but gives us much more detailed results. This can be used to separate volatile liquids or gases. Again, you will have a column packed with solid, and gas will pass over it at high temperature and high pressure. The retention time can be used for identification of the samples.
Now we're looking at TLC, so I've got my tablet of aspirin which I've crushed with a pestle and mortar here. I've got my TLC plates, and the particular plates that we use are shiny on one side and matte on the other side. It is the matte side that we want to be using. And the first thing we need to do, and you should really be doing this with a ruler, is about 1 centimetre up you need to draw a pencil line. So now I've dissolved my aspirin of ethanol, and I have my dots drawn in pencil at the bottom of my TLC paper. I have in my hand here a little bit of capillary tubing. This is very, very fine open tubing, and what I'm going to do is just pick up some of the aspirin in the tube, the aspirin solution in the tube. Because it's capillary tubing, it should run up the tube a little bit, and then I'm going to dot it onto spot number 1. Now, you'll need to do this quite a few times, allowing it to dry in between each time. The reason we'll allow it to dry and do it quite a few times is because if you just do a lot in one go, you'll get a big splodge, whereas we want a tiny concentrated splodge. So do a little bit, let it dry, do a little bit, let it dry, do a little bit, let it dry, and then you get the tiny concentrated splodge that'll give us the best results. So now I have my TLC plate in my chamber. I'm just going to put a lid on top of this to make sure that none of my solvent evaporates. Now I just want to point out that here I actually have a little bit of a gap in my lid. If you can find beakers where you don't get a gap, that'll work much better. Now you can see the solvent is just moving past my start line there, and as it moves past the start line, it's going to start to take some of the dissolved samples up with it. We need to wait until it gets about 1 centimetre on the top, and then we can stop. Okay, so after you've developed it, you're going to get something that looks like this. I will admit this isn't the plate that I just showed you because our UV light is broken at the moment, but you'll get big blobs that look like this. They're probably slightly elongated and in irregular shape. And you want to measure from the middle of this blob down to here. And we can use this value to calculate the RF value.
Ouch! This is why in some videos I have unexplained scratches.